Hello, and welcome to Sleep Gravity. For the time ahead, let the unfinished concerns of today drift gently into the background. You do not need to remember every number or every name. Simply listen, relax, and allow us to travel a little farther into the solar system, to a place where sunlight has grown much weaker and the distances between worlds are so vast that every motion seems to slow. We begin with Pluto, a small world once regarded by many as the final point in the solar system. In familiar diagrams, the planets are often arranged in a line extending outward from the Sun. Earth lies in the brighter, warmer region, followed by the large outer planets, and finally Pluto, appearing as a tiny dot near the edge of the image. Beyond it, there is often nothing but a dark background. This way of presenting the solar system makes it easy to imagine Pluto standing alone where everything ends. It can seem as though, once we pass beyond its orbit, we leave the realm of the planets behind and step directly into the space between the stars. But the real solar system does not end as neatly as a diagram. Pluto is not alone beyond the orbit of Neptune. It moves within a vast region filled with countless icy bodies. This area is known as the Kuiper Belt, and Pluto is only one of the largest, brightest, and most famous members we have discovered there. Beyond Pluto are objects far smaller than Pluto itself, some no more than irregular masses of ice and rock. Others are large enough for gravity to pull them into nearly round shapes, making them candidates for dwarf planet status. Some have moons orbiting them. Some have dark red surfaces, while others are so dim that they reflect only a tiny fraction of the light that reaches them. Scientists believe the region beyond Neptune may contain millions of objects. This does not mean that millions of Earth-like planets are waiting there. Most may be only a few kilometers, or a few dozen kilometers, across, with no oceans, continents, or thick atmospheres. Even so, each one is a real place, with its own shape, composition, surface, and path around the Sun. Some have followed their orbits for more than 4 billion years, since before Earth had stable oceans, before life appeared, and long before human beings began looking upward and wondering what might lie in the distance. At such distances, time seems to move to a different rhythm. A single orbit around the Sun can last for hundreds of years. Each season, if an object has clearly defined seasons at all, may continue longer than a human lifetime. While many generations on Earth are born, grow old, and disappear, a world beyond Pluto may complete only a small fraction of its journey around the Sun. Yet that same remoteness makes these worlds extremely difficult to see. Pluto and the objects around it do not produce their own light. They become visible only when sunlight reaches their surfaces, and a very small portion of it is reflected back toward Earth. The farther sunlight travels, the more widely it spreads and the weaker it becomes. If an object is small, dark, and billions of kilometers away, the returning light may be so faint that even through a telescope it appears as little more than a dim point. For this reason, the fact that we have not seen an object does not mean it does not exist. Sometimes it is simply too distant, too dark, or located in a part of the sky that has not yet been surveyed deeply enough. This is an important part of the story of the outer solar system. On older maps, the space beyond Pluto appears almost empty, but that emptiness reflects the limits of our instruments, at least as much as it reflects the true nature of space. For many decades after Pluto was discovered in 1930, astronomers found very few similar objects. Pluto was therefore treated as an isolated case. It was much smaller than the giant planets farther inward, and its orbit was more tilted and elongated. With no clearly recognized population to place it among, Pluto remained at the end of the planetary list as a deeply unusual member. Only much later, as telescopes became more sensitive and electronic detectors learned to record fainter points of light, did the picture begin to change. Other objects beyond Neptune were discovered one by one. At first, they appeared as only a few tiny specks, but over time their numbers grew, and scientists gradually realized that Pluto was not a solitary exception. It belonged to a population. That discovery did not make Pluto less special. Instead, it opened a more interesting way of seeing it. Pluto was no longer simply the final world in a list. It became a representative of an entire region of the solar system that humanity had only begun to understand. There, small bodies still preserve traces from the era when the planets were forming. Closer to the sun, higher temperatures, violent collisions, and geological processes transformed much of the original material. But in the cold region beyond Neptune, many icy bodies may have escaped such extensive change. This makes them remnants of an unimaginably distant past. They are not fossils in the ordinary sense, but the material within them may help scientists understand how the solar system began, how small objects came together, and why some regions eventually formed planets while others were left with countless scattered bodies of ice. So when astronomers observe a faint point of light beyond Pluto's orbit, they are not merely searching for another object to name. They are looking for a small piece of the history that formed Earth and the other planets around us. And yet, most of this region remains unseen in any clear way. We now know of many objects beyond Neptune, but compared with the number that may exist, those we have found are still only a small fraction. Some have never appeared in any image. Others may already have been recorded, but their light is too faint to be recognized among the countless points scattered across the sky. They do not disappear simply because they remain unknown. They continue along their long orbits, moving quietly through the darkness without any need for a human name or a human observer. This thought makes the solar system feel much larger than the familiar picture suggests. It is not only the Sun and 8 major planets, with Pluto beyond them as a final dot. Past Neptune's orbit lies an entire realm with its own structure, different groups of objects, immense orbital paths, and many questions that still have no clear answers. Even the word edge becomes difficult to use. The solar system has no sharp boundary where everything on one side belongs to the Sun and everything on the other instantly becomes interstellar space. The Sun's influence gradually weakens with distance, and objects may continue orbiting it far beyond Pluto. Pluto, then, is not truly the end. It simply lies near the place where simplified maps often stop, while the real solar system continues far beyond. In this journey, we will move deeper into that darkness. We will explore why people once believed Pluto stood alone, how the first objects of the Kuiper Belt were discovered, and why scientists can be confident that millions of bodies remain out there even though most have never been observed directly. The question that will follow us is not only what lies beyond Pluto. The deeper mystery is why such an enormous region of our own solar system could remain hidden from human sight for so long, and what those quiet worlds may still preserve from the distant past of the cosmic home in which we live. To begin, we will return to the time when Pluto had just been found, when that faint point of light seemed to stand alone before the darkness. From that imagined solitude, the story of millions of unseen worlds would slowly begin to unfold. When Pluto was discovered in 1930, it did not appear as the answer to a question about the Kuiper Belt. At the time, no one had a clear picture of the vast population of objects beyond Neptune. Pluto was found during a search for something else, a large unknown planet believed to be quietly influencing the orbits of worlds that had already been observed. This idea was commonly associated with the name Planet X, an unidentified planet thought to be hidden somewhere in the darkness of the outer solar system. Astronomers believed that small irregularities in the motions of Uranus and Neptune might point to a gravitational force that had not yet been fully explained. If a sufficiently massive object were concealed at a great distance, it could gently pull on the planets and leave traces in their orbits, even if the object itself had never been seen. Within the scientific understanding of that era, this was a reasonable idea. Neptune itself had been discovered after mathematicians used irregularities in the orbit of Uranus to predict the position of an unknown planet. That success encouraged many people to hope that the same method could continue extending the map of the solar system. At Lowell Observatory in Arizona, the search for Planet X involved photographing the same region of sky on different nights, then comparing the images to identify any point of light that had changed position. The work demanded immense patience. Each photographic plate contained countless stars, and most appeared almost identical from one night to the next. The observer had to examine one small area at a time, switching back and forth between two images while searching for a tiny point that seemed to move. Much of this work was carried out by Clyde Tombaugh, a young man raised in a farming family who was largely self-taught in astronomy. When he arrived at the observatory, he was not yet a famous scientist. His task was to operate the telescope, photograph the sky, and spend long hours at an image comparison device that displayed two photographic plates in rapid alternation, allowing a moving object to flicker into view. After months of observation, Tombaugh noticed in February 1930 that one point of light had shifted between two photographs taken in late January. The movement was very slight, but it was enough to show that the object was not a distant star. It lay within the solar system and was following its own orbit around the sun. The news spread quickly. A new world had been discovered beyond Neptune, and before long, it was given the name Pluto. At first, the discovery seemed to fit expectations surrounding Planet X. Pluto appeared in the region of sky where the search had been focused, and it was distant enough to become the newest and outermost member of the planetary family. But as astronomers began making more precise measurements, a problem emerged. Pluto was far smaller and less massive than the large planet they had imagined. Determining Pluto's size was not easy in the beginning. It appeared only as a point of light, and an object's brightness does not automatically reveal how large it is. A small world with a bright surface can reflect more light than a much larger object with a very dark one. Because Pluto's reflectivity was not yet known, early estimates varied considerably. Over time, improved observations caused the estimated size of Pluto to shrink again and again. Then, in 1978, the discovery of its large moon Charon allowed scientists to calculate the mass of the Pluto system more accurately. The results showed that Pluto could not possibly be massive enough to produce the gravitational effects once attributed to Planet X. A new world had indeed been found, but it was not the giant planet people had imagined hiding in the darkness. This created an unusual situation. Pluto had been discovered through a search based on assumptions that ultimately did not hold up, yet the discovery itself was entirely real. The orbital irregularities once used to infer the existence of Planet X were later explained largely through more accurate measurements, especially after Neptune's mass was revised. Pluto was not responsible for those apparent disturbances. Tombaugh had simply been looking at the right region of sky at the right moment, and recognized a world that no one had previously distinguished. For many decades after its discovery, Pluto remained alone. No other large body resembling it was confirmed near its orbit. This made Pluto difficult to classify, but it also protected its special status. It was called the ninth planet, even though it differed clearly from all the others. The four inner planets are composed mainly of rock and metal. The four giant planets farther out are enormous, with compositions rich in gas or ice. Pluto, by contrast, is smaller than Earth's moon, follows an orbit tilted significantly from the common planetary plane, and travels along a more elongated ellipse. During part of its orbit, Pluto is even closer to the Sun than Neptune, although the two worlds cannot collide because their motions are arranged within a stable gravitational relationship. These characteristics made Pluto seem like an unusual visitor placed at the end of a family that otherwise had a fairly clear structure. Yet without any known population to which it fit more naturally, astronomers had little reason to view it differently. Although Pluto still appeared alone on the map, the possibility that many smaller objects might exist beyond Neptune had begun to enter the thinking of some researchers. The solar system was believed to have formed from a disk of gas and dust surrounding the young sun. Within that disk, material collided, joined together, and gradually formed larger bodies. Some regions developed into planets, but it was unlikely that this process had used every piece of the original material. If asteroids remained between the orbits of Mars and Jupiter, and comets still appeared from distant regions from time to time, then it was reasonable to imagine that a reservoir of material might also survive beyond the giant planets, never having gathered into a single large world. Several astronomers, including Kenneth Edgeworth and Gerard Kuiper, discussed possibilities involving small bodies in the outer solar system. Their ideas were not identical to the modern scientific picture of the Kuiper Belt, nor did they provide an exact map of the region. Even so, their speculations reflected a question that was becoming increasingly difficult to ignore. Was Pluto truly the only surviving object beyond Neptune? Or was it simply the first member bright enough for human beings to see? This question was also connected to the origin of short-period comets, which return to the inner solar system after intervals of a few decades or a few centuries. Their orbits suggested that they were unlikely to come only from a spherical reservoir at an extremely great distance. There seemed to be a closer, flatter source, one more closely aligned with the orbital plane of the planets. A population of small bodies beyond Neptune could explain this. From time to time, the gravity of the giant planets could alter an object's orbit, gradually sending it inward through the solar system. As it approached the Sun, ice on its surface would begin to sublimate, forming the bright head and familiar tail of a comet. From this perspective, some of the comets that appear in the night sky may have spent most of their history in the frozen region beyond Pluto. They became easier to see only after their orbits were disturbed and carried them closer to the light. But a plausible idea is not the same as direct observational evidence. For many years, these proposed objects remained elusive through telescopes. They appeared in models of solar system formation and theories about the origins of comets. Yet on observational maps, the region beyond Pluto still looked almost empty. This was not because astronomers lacked interest. The technology of the time was poorly suited to conducting deep surveys across broad areas of sky. Traditional photographic plates had limited sensitivity. Comparisons were performed mainly by eye, and searching for extremely faint points of light required an enormous amount of observing time. A survey could continue for years and still cover only a small portion of the sky. Pluto was discovered partly because it is relatively large, reflects enough light from its surface, and happened to lie within the reach of a persistent observing campaign. Smaller bodies would be far more difficult to find. Even if they existed in great numbers, each individual object could still be too faint to appear clearly on a photographic plate. As a result, during the second half of the 20th century, a significant gap remained between what scientific models suggested and what telescopes could actually see. Theory gave researchers reason to suspect that a distant population might exist. Comets offered indirect clues. Pluto stood as a single example, but one object alone was not enough to prove that an entire realm of bodies was orbiting the Sun. The silence of the sky continued for so long that Pluto gradually became familiar through its very isolation. It appeared in books, models, and the human imagination as the final world, not because science had shown that nothing existed beyond it, but because humanity had not yet found a way to look deeply enough into the darkness. By the closing years of the 20th century, that situation began to change. More sensitive electronic imaging devices gradually replaced traditional photographic plates. Computers could store, process, and compare vast amounts of data that people had once been required to examine by eye. Points of light too faint for older surveys finally had a chance to emerge. By then, the questions surrounding Pluto had remained unanswered for more than 60 years. Was it truly a unique object, or merely the first visible member of a hidden population? The answer did not arrive as a large, bright, easily recognizable world. It appeared as an exceedingly faint point of light, moving very slowly against the background stars. At first glance, there was nothing remarkable about it. But once its orbit was confirmed, the darkness beyond Pluto changed forever. The world that had once stood alone was about to gain its first neighbor. For more than 60 years after Pluto was discovered, The region beyond Neptune remained almost empty on astronomical maps. Scientists had many reasons to believe that other objects must exist there, yet telescopes revealed very little. Pluto continued to appear as a rare and unusual case, small and distinctive, moving alone in a place where the familiar planets had already fallen far behind. The problem was not a lack of searching. Some astronomers spent years observing regions of sky near the orbital plane of the planets, where distant bodies were most likely to appear. They photographed the same area at different times, then compared the images in search of a point of light that had shifted. The process sounded simple, but most of the time it produced photographs that looked almost exactly the same. Among thousands of stars, an object beyond Neptune carried no obvious feature that would make it stand out immediately. It was too distant to appear as a clearly defined disk, too small to reflect much light, and moving so slowly that its change in position was sometimes barely noticeable. Some nights of observation ended without a single reliable candidate. Other points of light seemed to have moved, only to turn out to be detector noise, a flaw in the image, or a source that could not be confirmed again. David Jewett and Jane Liu continued this search patiently for years. They could not know whether they would uncover an entire population of objects or simply keep receiving silent frames of sky. Although models of solar system formation and the origins of comets suggested that leftover material might exist beyond Neptune, direct evidence had yet to appear. Then, in August 1992, within data collected at Mauna Kea in Hawaii, one extremely faint point of light was no longer standing still. It did not appear as a new world in the close-up images we are familiar with today. There was no horizon, no shadow, and no visible detail on its surface. In each frame, it was only a tiny speck among many others. Only when the images were placed side by side did the difference become clear. The background stars remained fixed, while this point of light had moved a short distance. That motion showed that the object was much closer to us than the stars and was orbiting the Sun. Follow-up observations confirmed that its path lay beyond Neptune. The object received the provisional designation 1992 QB1 and, many years later, was given the name Albion. Albion was far smaller than Pluto. It was not the missing large planet once imagined on the map, nor was it visually striking enough to attract immediate public attention. Yet the importance of the discovery did not lie in the object's size, but in its location. For the first time since Pluto and its moon Charon, another body had been confirmed moving through the distant region that humanity had previously known only through speculation. Pluto finally had a clearly observed neighbor. A single discovery was still not enough to prove that an entire belt of objects existed. Albion might have been another rare exception, a lone remnant that happened to survive on a distant orbit. But astronomers now had evidence that small bodies beyond Neptune were more than features in theoretical models. At least one had appeared in the data, and once one object had been found, the possibility that many more remained immediately became far more compelling. Just as important, the discovery showed that observational technology had finally become sensitive enough. New electronic detectors could record fainter sources of light than traditional photographic plates. The data were also easier to store and compare, allowing researchers to recognize tiny motions that might previously have gone unnoticed. After 1992, the sky beyond Neptune did not remain silent for long. New objects were discovered one after another in the years that followed. At first, each name added only another point to the map. But as their numbers grew, their meaning began to change. These were no longer a few scattered exceptions surrounding Pluto. They were beginning to reveal the presence of a genuine population. The newly found bodies were not all alike. Some traveled on relatively stable orbits close to the region astronomers had expected. Others followed longer, more tilted paths. Some appeared to be strongly influenced by Neptune's gravity. These differences could not be explained immediately, but they showed that the outer region was not a simple ring of icy bodies arranged evenly around the Sun. It was a realm with structure, a history, and billions of years of change behind it. At first, the most striking development was still the fundamental shift in perspective. Previously, if Pluto seemed unusual, it was possible to assume that it was simply an unconventional planet. But as new objects appeared, another explanation gradually became more reasonable. Perhaps Pluto was not a major planet, strangely placed in the distant reaches of the solar system. Perhaps it was a large member of a group of bodies that humanity had only just begun to recognize. This difference may sound like a matter of classification, but it changed the entire picture of the solar system. If Pluto belonged to a vast population, then the region beyond Neptune could no longer be treated as a faint appendage lying behind the planets. It had to be understood as a distinct domain, made up of objects with related origins and shaped by gravitational processes stretching back to the youth of the solar system. Albion and the bodies discovered after it also created a very different sense of distance. For billions of years, they had continued orbiting the sun without any living creature on Earth knowing they existed. They were already there while Earth's surface was still undergoing immense change, while life was only beginning, and long before human beings appeared to give names to the stars. The year 1992 was not when Albion was born or entered the outer solar system. It was simply the moment when light reflected from its surface was finally recorded by an instrument sensitive enough to detect it, and when its tiny movement was noticed by two astronomers. The discovery reminded us that an empty space on a map is not necessarily an empty place in nature. Sometimes it is only a region that human vision has not yet reached. A world may exist within an area of sky that has been observed many times and still remain unrecognized because it is too faint, moves too slowly, or appears under conditions that make it difficult to detect. As surveys continued, the list of objects beyond Neptune gradually grew longer. Each newly measured orbit helped scientists understand more about the extent of this population. At the same time, every discovery made the question larger. If telescopes in the early 1990s could already find so many small bodies, how many fainter objects still remained below the limit of observation? Perhaps the first discoveries represented only the most visible part of a vast population, like the highest peaks emerging before an entire mountain range can be recognized through the mist. Larger and brighter members, or those passing closer to the sun along their orbits, would be more likely to be found. Behind them could lie an enormous number of smaller, darker bodies that the telescopes of the time were still unable to record. From a single point of light confirmed in 1992, astronomers began moving toward the idea that the region beyond Pluto contained more than a few scattered worlds. It might hold hundreds of thousands of large objects, along with millions of smaller icy bodies, all continuing to orbit the sun according to the slow rhythm of the distant solar system. But before their numbers could be estimated, science first had to understand how far this region truly extended. Were these objects arranged in a belt, as the familiar name suggests, or were they distributed through several more complex layers? Had Neptune kept them in place, or had that same planet once driven a large part of the population away from its original location? The discovery of Albion answered the first question. Pluto was not alone. What followed was far more difficult, because it required humanity not only to find more points of light, but to assemble their orbits into a meaningful map. The outer solar system had finally begun to emerge. Yet the more detail astronomers uncovered, the clearer it became that this region was nothing like a simple ring of ice surrounding the sun. Behind the name Kuiper Belt lay a vast, layered structure that gravity had been rearranging for a span of time longer than nearly the entire history of Earth. As the number of objects beyond Neptune began to grow, astronomers needed a way to describe the new region of space emerging before them. The name Kuiper Belt gradually became familiar, and the word belt alone suggested a fairly clear image, a broad ring of ice and rock, neatly arranged beyond the orbit of the most distant planet. That image is useful as a starting point, but on closer inspection, the outer solar system is nowhere near so orderly. Its objects do not all follow the same circular path, nor are they evenly distributed like grains of dust across a disk. They travel on many different orbits, tilted at different angles, and are influenced by Neptune in ways that have endured for billions of years. To describe these distances, Astronomers often use the astronomical unit, abbreviated as AU. 1 AU is the average distance between Earth and the Sun, nearly 150 million kilometers. Neptune lies about 30 AU from the Sun, while Pluto's average distance is close to 40 AU, although its elongated orbit causes that distance to change considerably over the course of a single revolution. The most densely populated part of the Kuiper Belt begins not far beyond Neptune's orbit and extends to roughly 50 AU. On a diagram, that span may appear only a few centimeters wide, but in space, it represents billions of kilometers. Light takes many hours to cross the region, while a small object may require centuries to complete a single orbit around the Sun. Even within this enormous expanse, the objects do not form one uniform group. Some travel on relatively circular orbits, maintaining a fairly steady distance from the Sun. These are commonly placed in the classical Kuiper Belt. The word classical does not mean that they are simple or familiar. It merely indicates that their orbits are less elongated than those of many other groups. Objects in this population move through a relatively stable region beyond Neptune. Some follow paths tilted only slightly from the common plane of the planets, while others are inclined much more steeply. These differences offer clues about the past, because a population with flat, orderly orbits often suggests that it experienced less disturbance, while tilted or elongated paths may preserve traces of stronger gravitational interactions. In the outer solar system, an orbit is a kind of record left behind after a period of upheaval. An object cannot describe what happened to it in words, but its path around the Sun can reveal how it may once have been pulled, pushed, or displaced. Pluto belongs to a different group. Its orbit is more elongated and at times carries it closer to the Sun than Neptune. This once led many people to wonder whether the two worlds might ever approach each other too closely. On a two-dimensional diagram, their orbital paths seem to cross, but in reality, their motions are held within a remarkably stable gravitational rhythm. Pluto completes 2 orbits around the Sun during roughly the same period in which Neptune completes 3. This relationship is known as a 3-to-2 orbital resonance. The term may sound technical, but its meaning is fairly easy to picture. The two bodies do not move at random. Their positions repeat in a regular rhythm, like two motions traveling at different speeds but always returning to the same order after a certain length of time. Because of this arrangement, whenever Pluto passes through the part of its orbit that lies near Neptune's distance from the Sun, the giant planet is always safely positioned far away. Their paths may appear to touch on a map, but the two worlds never reach the crossing point at the same time. Pluto is not the only object held in a 3-to-2 resonance. Many other bodies follow a similar rhythm and are commonly called Plutinos, meaning objects whose orbital relationship closely resembles Pluto's. The existence of an entire group like this shows that Neptune has played an important role in arranging the outer solar system. There are other resonances beyond the 3-to-2 pattern. Some objects complete 1 orbit while Neptune completes 2, and still others follow different ratios. There is no need to remember each number to understand what is happening. The important point is that Neptune's gravity does more than tug at objects as they pass nearby. Over immense periods of time, it can hold them within stable patterns of motion, creating distinct orbital groups. The Kuiper Belt, then, is not a place entirely beyond the influence of the planets. Neptune remains present within its structure, even though the distances between individual objects may be enormous. The planet's gravitational signature is written into the motion of many small worlds, like a melody so slow that its repeating pattern can be recognized only through years of observation. Not every object is held in such a stable orbit. Some follow elongated ellipses that bring them close to Neptune's region at one point and carry them much farther away at another. These bodies are often associated with the scattered disk, a region whose boundaries are less clearly defined than those of the classical Kuiper Belt. The word scattered partly describes their history. During the early solar system, before the giant planets had fully settled into their present positions, close gravitational encounters may have pushed small bodies onto longer, more steeply tilted orbits. Some were thrown out of the solar system entirely. Others moved inward and may have become comets. Still, others remained bound to the sun, but on such vast paths that they spend most of their time at tremendous distances. For this reason, the farther outward we travel, the less accurate the word belt becomes. The region does not end at a sharp boundary. Its population gradually thins, the orbits become more varied, and some bodies travel far beyond the area usually considered part of the Kuiper Belt. This also makes the idea of being beyond Pluto more complicated. Pluto does not sit at a fixed line dividing one region from another. During one part of its orbit, it is closer to the Sun, while at other times it travels farther away. Many objects may lie beyond Pluto during one period and closer to the Sun than Pluto during another. When orbits last for centuries, arranging worlds in a straight line from nearest to farthest becomes little more than a temporary simplification. The solar system is not like a row of objects placed permanently on a shelf. It is a system in motion, where relative positions are always changing and distance has meaning only when connected to a particular moment in time. The first discoveries of the 1990s revealed only that a population existed beyond Neptune. It was not until their orbits had been followed for longer periods that astronomers realized this population was divided into several groups. Each one seemed to preserve a different part of the history of the outer solar system. Objects with nearly circular orbits may have escaped the strongest interactions. Resonant bodies reveal Neptune's long-lasting influence. The elongated paths of the scattered disk point toward a more turbulent past, when the giant planets may have migrated through the original disk of material and altered the trajectories of countless smaller bodies. This picture is far removed from a quiet ring of ice resting beyond Pluto. The region has been shaped and reshaped by gravity, even if its most dramatic changes ended long ago. What remains today is like a surface that has settled after a period of upheaval, while the older traces are still preserved within every orbit. What is remarkable is that these orbits are determined from points of light so small that their shapes cannot be seen at all. Astronomers track the position of an object over many nights, months, and sometimes years. From the short arc they are able to observe, they calculate the much wider orbit that the body may take hundreds of years to complete. At first, a new discovery usually comes with considerable uncertainty. With only a handful of observations, it is impossible to know exactly how far the object will travel or when it will return. As more data accumulate, its orbit gradually becomes clearer, and the small world can be placed within the proper group in the structure of the outer solar system. There is an interesting contrast here. The objects move slowly, but understanding them also takes time. A single observation can never reveal the whole path. Astronomers must return, record new positions, and wait until a small enough portion of the orbit becomes clear enough to reveal the shape of the entire journey. As in many other areas of astronomy, patience becomes an instrument of observation. As the map of the Kuiper Belt gradually took shape, scientists noticed another unusual feature. The density of objects did not continue evenly outward without end. Beyond a certain distance, the number of bodies belonging to the classical region dropped quite noticeably. This area is sometimes described as the outer edge of the main Kuiper Belt. That decline raised further questions. Had the original material simply been concentrated only as far as that point, or had some gravitational process removed what once lay beyond it? Could passing stars have disturbed the outer region when the sun was young? Or had the giant planets shifted in ways that drove most of the material away from its original orbits? Today, models of giant planet migration play an important role in explaining this structure. According to these models, Neptune may not have formed exactly where it is now. Early in the solar system's history, it may have moved outward through a disk filled with countless small bodies, altering their orbits as it went. Some objects were captured in resonances, others were scattered farther away. Some may have been pushed inward or expelled from the solar system entirely. What remained became the complex population we observe today. If this is correct, The Kuiper Belt is more than leftover material from the formation of the planets. It is also evidence that the planets themselves once changed position. The young solar system was not a finished structure assembled in place and left unchanged for more than 4 billion years. The planets may have migrated, interacted, and rearranged the regions around them before settling into the relatively stable configuration we see today. From Earth, everything appears quiet. Neptune continues along its long orbit. Pluto and the smaller bodies move too slowly for the human eye to notice. Yet this present calm conceals a history filled with motion. Each orbital group in the Kuiper Belt is like a surviving fragment of that history. It is not a complete record, but it is enough to show that the outer region once underwent profound change. To read that record, scientists must combine thousands of individual paths into a single shared story. And that story leads to something even more remarkable. If the Kuiper Belt was once stirred and scattered by Neptune, then the objects remaining today may represent only a small fraction of the original population. The millions of bodies we have yet to see may once have been far more numerous before the giant planets rearranged the outer solar system. The space beyond Pluto is therefore not only vast, but layered, extending from relatively undisturbed orbits to elongated paths reaching into the scattered disk. These layers are not separated by sharp boundaries. They blend into one another through distance and motion. By this point, the Kuiper Belt is no longer simply a name for everything beyond Neptune. It has become a structure that must be read through orbits, with each small object preserving part of the information about events that unfolded more than 4 billion years ago. But to understand why this region still contains so many ancient bodies of ice, we need to return to a time before Pluto, Neptune, or even Earth had taken their final forms. The Sun had only recently formed. A vast disk of material surrounded it, and the first worlds were just beginning to be built from countless tiny grains of dust. The complex orbits within the Kuiper Belt show that the outer solar system was never completely calm from the beginning. The objects there were pulled inward, pushed outward, captured in stable rhythms of motion, or scattered onto paths of enormous length. But before Neptune rearranged this distant region, another story had already begun, one that unfolded more slowly and started with particles of matter so small they are almost impossible to imagine. About 4.6 billion years ago, the Sun had just formed within a vast disk of gas and dust. There was no Earth, no Pluto, and none of the clearly defined orbits we see today. Surrounding the young Sun were countless particles moving together, colliding, separating, and joining again through a process that continued for millions of years. The planets did not appear all at once. They grew from very small beginnings. Grains of dust clung together to form larger clusters, and those clusters continued to meet and combine into bodies of increasing size. Once an object became large enough, its gravity began holding more material nearby, allowing its growth to accelerate. In the inner solar system, where temperatures were high, durable materials, such as rock and metal, became the main building blocks. These were the materials that formed Mercury, Venus, Earth, and Mars. Farther out, lower temperatures allowed water and many other volatile substances to remain frozen, increasing the amount of solid material available and helping the giant planets develop. Beyond the present orbit of Neptune, a similar process was also taking place. Particles of ice and rock met, combined, and gradually formed larger bodies. Some eventually became Pluto, Eris, and other dwarf planets. Many smaller objects grew to tens or hundreds of kilometers across, large enough to survive through nearly the entire history of the solar system. If so much material once existed there, a natural question arises. Why did it not all come together to form another large planet? The first part of the answer lies in distance. The farther an object is from the Sun, the wider its orbit becomes and the longer it takes to complete a revolution. Small bodies moved through a much larger volume of space, so they encountered one another less often. Material continued to accumulate, but far more slowly than it did closer to the Sun. The density of matter was also lower than in the regions where the major planets formed. A body of ice could complete many orbits without encountering enough material to grow significantly. Over long periods, some objects still became larger, but the outer region would have needed far more time to combine into a single major planet. And that time may simply have run out. As the giant planets formed, their gravity began influencing the rest of the surrounding disk. According to current models, Neptune may not have originated exactly where it is today. Early in the solar system's history, its orbit may have gradually shifted outward, carrying the planet into a region filled with countless icy bodies. This migration did not happen as one sudden leap. It resulted from an enormous number of small gravitational interactions, but their combined effect on the outer solar system was profound. When a small object passed near Neptune, its orbit could be altered. Some bodies were captured in stable rhythms and remained there. Others were pushed onto longer, more tilted, or more distant paths. Some were sent inward through the solar system, while others may have been ejected from it entirely. Over time, the once densely supplied region became increasingly sparse. The remaining objects were not only fewer in number, but also spread across wider orbits, making further collisions and mergers less likely. The Kuiper Belt today is therefore not a region waiting to finish building another planet. That process nearly came to a halt long ago. What we observe is what remained after the giant planets transformed the original structure of the outer solar system. The Kuiper Belt is sometimes described as a planet that never had the chance to form, but that phrase captures only part of the story. Its objects did not simply remain beside one another and fail to merge. Their environment was disrupted before their growth could continue much further. Most of the available material was scattered, while the surviving bodies were placed on orbits that rarely allowed them to meet. Yet that interruption helped preserve a great deal of information about the earliest period of the solar system. When a large planet forms, the material inside it may be compressed, heated, melted, and rearranged. Its deeper layers change, its surface is renewed, and many of its earliest traces gradually disappear. On Earth, geological activity, water, and life have continuously transformed the surface for billions of years, making much of its earliest history difficult to read. The small objects beyond Pluto have not remained entirely unchanged. They have been exposed to radiation, collisions, and slow alterations across their surfaces. Even so, most are not large enough to experience the powerful geological activity found on planets. Their low temperatures and great distance from the sun have also helped them preserve ices and compounds that were lost or deeply transformed in warmer regions. Each small body may therefore hold a different part of the past. A nearly round object shows that it once grew large enough for gravity to pull its material toward the center. An irregular body may never have reached that size. Some objects consist of two parts joined together, suggesting that they touched gently rather than colliding violently. Others have moons, revealing histories that may have included more complex encounters. Even color carries information. Some bodies are brighter because their surfaces contain highly reflective ice. Others have grown darker and redder as radiation altered surface compounds over immense periods of time. From Earth, they all appear as tiny points of light, but they are not identical copies of one another. Each world has followed its own path. Some may have formed close to where they are now. Others may have originated elsewhere and later been carried into new orbits by gravity. Certain bodies have experienced collisions, losing material or creating families of fragments. Still, others appear to preserve the light, porous structures they acquired during the earliest stages of formation. By placing all these clues together, scientists can gradually reconstruct the ancient outer solar system, not through a single image, but through a combination of the shapes, colors, compositions, and orbits of many different objects. This is why even a very small body can be enormously valuable. It does not need to be the size of Pluto to tell an important story. An icy object only a few dozen kilometers across may preserve a kind of structure that larger worlds lost long ago. In this sense, The millions of objects beyond Pluto are more than a vast collection of rock and ice. They are like separate fragments of the same memory, preserved after the construction of the solar system came to an end. The outer region once contained more material, more encounters, and more opportunities for worlds to continue growing. But as Neptune migrated and the original population was scattered, that process slowed and nearly stopped altogether. Pluto and the bodies around it are not worlds still on their way to becoming planets. They are survivors from an age when that path was still open. Today, the distances between these objects have become immense. Powerful collisions are less common, their movements unfold at a slow rhythm, and the outer region appears almost motionless. Yet that stillness is only its present state. Beneath it remain the traces of a young solar system that once shifted the positions of planets and scattered countless bodies onto new orbits. To understand more clearly what has been preserved, we need to look more deeply at these distant surfaces themselves. The ice beyond Pluto does not exist in only one form, and the faint colors recorded by telescopes can reveal what these worlds are made of, what they have experienced, and why they are far less alike than their distant appearance might suggest. From Earth, most objects beyond Pluto do not appear as worlds with mountains, valleys, or clearly defined horizons. Even through large telescopes, they usually remain no more than tiny points of light, mixed among countless background stars. Yet a point of light is not necessarily an empty image. The light reflected from the surface of a distant body carries traces of the place it has just touched. Although only a very small amount returns to Earth, it may still contain information about color, surface ice, and changes that have unfolded over billions of years. This is how the worlds beyond Pluto began to acquire individual identities, long before humanity could ever see them up close. When people imagine a frozen region, they often picture the color white. But the Kuiper Belt is not a realm of identical, brightly shining blocks of ice. Some objects reflect a considerable amount of light, while others are so dark that they nearly disappear into the background of space. Some appear pale gray, while many others display distinct shades of red or reddish-brown. These colors do more than give each surface a different appearance. They reveal that the material on every world has passed through a history of its own. In the outer solar system, temperatures are low enough for many substances that exist as gases on Earth to freeze onto the surface. Methane, nitrogen, and carbon monoxide can form broad layers of ice, while frozen water becomes hard and durable, behaving almost like rock. On smaller bodies, ice may be mixed with dark dust, stone, and carbon-rich compounds. Over time, these surfaces are continually exposed to radiation from the sun and to high-energy particles arriving from space. These effects are weak but persistent, and they can alter molecules, join them into more complex mixtures, and gradually turn the outer surface a deep shade of red. This process does not require life. It needs only the right materials, radiation, and enough time. In a place where a single year may last for centuries, changes that would be almost impossible to notice within a human lifetime have more than enough time to reshape an entire surface. Pluto is the world that has allowed us to see this more clearly than any other object in the Kuiper Belt. Before the New Horizons flyby, astronomers already knew that Pluto was not uniform in color. Reflected light showed that some regions were brighter, others darker, and that the surface contained several different kinds of material. But when the spacecraft approached in 2015, the faint telescopic point finally opened into a complete world. The images it returned revealed vast bright plains, dark reddish-brown regions, and mountain ranges rising above the surface. Yet what made the landscape remarkable was not only the shape of its terrain. The materials forming that terrain were also very different from those familiar on Earth. On Pluto, water ice is hard enough to form the foundation of mountains. Frozen nitrogen, by contrast, is softer and can flow very slowly across the surface, much as glaciers of water ice move on Earth. Methane and other ices cover many regions, causing brightness and color to vary from one place to another. There, water behaves much like rock, while the substance that makes up most of Earth's atmosphere can lie across the ground as plains of ice. This reversal shows how completely temperature can change the way matter behaves. The same substance, under different conditions, may become a gas, a liquid, or part of the landscape itself. Pluto's surface is not entirely still. As this world follows its long orbit around the Sun, temperatures in different regions change slightly. Some ice may pass directly into gas, enter the thin atmosphere, and later freeze again in colder areas. Across seasons lasting many decades, material is slowly carried from one region to another. The colors seen by New Horizons are therefore not only traces of the distant past. Some are also shaped by changes that continue today, although they unfold too slowly to be observed in full over any short period of time. Worlds smaller than Pluto are often unable to retain a clearly defined atmosphere or sustain such complex cycles of ice. Even so, the light they reflect can still reveal what their surfaces are made of. To do this, astronomers look beyond overall brightness. They separate the light into different wavelengths, much as a prism divides white light into a spectrum of colors. This method is known as spectroscopy. When sunlight reaches a surface, some wavelengths are reflected more strongly, while others are absorbed by the material. Each type of ice leaves its own pattern of absorption. As a result, the light returning to a telescope may carry the signature of methane, water, ice, or other compounds, even when the object itself remains nothing more than a shapeless point. Scientists do not need to see the ice directly to recognize it. They can identify it through the portions of light that never returned. We might imagine this light as a very quiet voice traveling across a great distance. The sound has weakened, but some of its qualities remain clear enough to reveal where it came from. Spectroscopy works in a similar way. It does not bring the surface of a distant world into the laboratory, but it can reveal the kind of material the light encountered before beginning its journey back to Earth. Makemake offers a clear example. This world is smaller than Pluto and far too distant for its surface to be seen in detail. Yet its reflected light reveals the presence of frozen methane. Makemake also has a reddish-brown color and reflects light fairly well compared with many other objects in the region. We do not have close-up images showing mountains or plains on Makemake. Most of what we know comes from reflected light, its extremely faint thermal emission, and occasions when the object passes in front of a distant star. Even so, these measurements are enough to show that Makemake is not simply an anonymous block of ice. It has its own surface composition and has undergone a different process of change from Pluto. This also reminds us that two worlds containing methane do not necessarily resemble one another. Size, gravity, temperature, and orbital history can all affect how ice is distributed. One object may retain more volatile material, while another has lost most of it over time. In some places, the surface may be renewed by moving ice, while elsewhere it may remain exposed to radiation long enough to become darker and redder. Color, then, is only the beginning. It signals that surfaces are different, but cannot explain every reason by itself. Astronomers must combine many forms of observation. Brightness shows how efficiently an object reflects light. Color offers clues about its outermost material. Spectroscopy can identify certain kinds of ice. Thermal emission helps estimate size, while variations in brightness as the body rotates may reveal an uneven surface or a shape that is not perfectly round. Each measurement provides only one part of the picture. Placed together, they gradually form the portrait of a world that has never been clearly seen. These portraits, of course, still have limits. The light collected from a distant object is often a mixture from the entire portion of the surface facing Earth. If that surface contains several different regions, their signals blend together. A thin layer of ice may also conceal the material beneath it, allowing scientists to identify only the outermost covering. For small and dark bodies, the signal is weaker still. Sometimes repeated observations with several instruments are needed before a feature can be confirmed. Conclusions are therefore expressed with care. A surface may appear rich in water ice, or a signal may be consistent with methane, but this does not mean that the entire world is evenly covered by that material. This caution does not make the discoveries any less remarkable. Instead, it shows how astonishingly much information humanity can draw from only a few photons. A ray of light leaves the sun and travels for hours into the outer solar system. It touches the surface of a frozen world, then reflects back into space. After another long journey, a tiny fraction is gathered by a telescope. Within that faint light, traces still remain of the ice it once encountered. Each measurement like this gradually brings color to the Kuiper Belt. It is no longer merely a dark region filled with anonymous points of light, but a place of bright frozen plains, red surfaces transformed by radiation, and worlds preserving methane or water ice in different proportions. Not every body beyond Pluto is alike, because they were not formed or altered in exactly the same way. Each world has preserved its own part of the outer solar system's history, allowing that history to appear very faintly in reflected light. In the darkness between their orbits, these surfaces remain beneath a sun that has become little more than an intensely bright point in the distance. We have never touched most of them, nor have we seen their true landscapes. But a small amount of light has returned, enough to reveal that beyond Pluto there is more than nameless ice and rock. There are worlds with colors of their own, and every color carries a trace of matter, time, and a history that has yet to be fully read. From the faintest traces carried in reflected light, astronomers came to understand that the objects beyond Pluto are far from identical. Some have bright surfaces rich in ice, while others have turned deep red after billions of years of exposure to radiation. Some are little more than small, irregular masses of material, but others are large enough for gravity to shape them, retain moons, and develop surfaces far more complex than their appearance as distant points of light would ever suggest. Pluto was the first world to reveal this most clearly. For most of the time humanity had known about Pluto, we had never seen its true form. Through telescopes, it appeared only as a tiny point of light, sometimes changing slightly in brightness as it rotated. Measurements showed that its surface was not completely uniform, but no one knew what those light and dark regions actually were. Only when New Horizons flew past in 2015 did Pluto emerge in the full complexity of a world. Mountains of water, ice rose above the surface. Vast plains of frozen nitrogen, nearly free of impact craters, showed that some regions were far younger than expected. Layers of haze floated within its thin atmosphere, while different kinds of ice continued to move slowly with the seasons and changing temperatures. Pluto was not simply a leftover fragment of material, frozen completely in place since the solar system first formed. It had a geological history, distinct surface regions, and processes that were still continuing, even under conditions colder than almost anywhere familiar to human experience. Judged by that richness alone, Pluto fully deserves to be regarded as a world in its own right. For this reason, its removal from the list of the 8 major planets is sometimes described as a loss. But the real story did not begin because Pluto became less important. It began when humanity discovered that Pluto had never been alone. When Pluto was found in 1930, no one knew of the Kuiper Belt as we understand it today. Small objects beyond Neptune remained below the detection limits of most telescopes, while Pluto was the only body bright enough to be recognized. Within the picture available at the time, calling it the 9th planet was a reasonable choice. It orbited the Sun, lay beyond Neptune, and there was no other known population in which it could be placed more naturally. Beginning in the early 1990s, however, the emptiness around Pluto gradually began to fill. New objects appeared in the data, first only a few, then in steadily growing numbers. Some were very small, but others were substantial in size. With each discovery, Pluto's unusual nature became easier to understand. Its tilted and elongated orbit was no longer a feature without explanation. Its icy composition no longer seemed entirely unique. Pluto began to appear as a large member of a broad population rather than a solitary planet separated from every other group. Even so, the traditional classification might have remained unchanged if all the newly discovered bodies had been much smaller than Pluto. The true turning point came when another world was found farther away, following an orbit even longer and more steeply inclined. That world was Eris. Eris was identified in images taken in 2003 and announced 2 years later. It lies so far away that a single orbit around the Sun lasts more than 5 centuries. For most of that journey, sunlight there is only a tiny fraction of what Earth receives. Early measurements suggested that Eris was nearly the same size as Pluto, and it was even more massive. The discovery immediately raised a question that astronomy could no longer postpone. If Pluto was a planet, then Eris had just as much reason to be called one. And if a world nearly as large as Pluto had already been found, future surveys might reveal many more similar bodies. The list of planets would then no longer reflect a clearly defined natural structure, but could keep changing every time another large object was discovered. This did not mean that astronomers were afraid the solar system might contain too many planets. Nature does not need to arrange itself for the convenience of textbooks. The real issue was that a scientific category should reflect the relationships among objects, rather than relying only on size or order of discovery. Earth, Jupiter, and Neptune are all bodies whose gravity dominates their orbital regions. They are still surrounded by moons, asteroids, and many smaller objects, but these planets are the controlling masses within their local environments. Over billions of years, they have gathered, scattered, or organized most of the material near their paths around the Sun. Pluto exists in a different situation. It is large enough for gravity to pull it into a nearly round shape and complex enough to possess its own geology, but it remains a member of the Kuiper Belt. The space around Pluto's orbit is not controlled by Pluto alone. Many other bodies with related origins also occupy that broad region beyond Neptune. This is why Pluto and Eris are classified as dwarf planets. The name can easily create a misunderstanding. It may suggest that a dwarf planet is simply a planet that never became large enough, like a smaller version of Earth or Neptune. But size is not the only important factor. A dwarf planet is a world massive enough for gravity to shape it, yet it remains part of a broader population rather than becoming the dominant body throughout its orbital region. Seen this way, Pluto did not become a smaller object in 2006. Its icy mountains did not grow shorter, its atmosphere did not disappear, and its 5 moons continued orbiting just as before. What changed was the map surrounding Pluto, and as that map expanded, its true place within the solar system became clearer. Before, Pluto was the strangest planet in a group it never fully fit. After the Kuiper Belt was discovered, it became one of the largest worlds in a newly recognized family. That change did not make Pluto's story smaller. On the contrary, it gave Pluto a deeper kind of importance. It was no longer merely the final dot beyond the 8 planets. It became a representative of an entire region that humanity had once known almost nothing about. The same is true of Eris. Its significance lies in more than the way it made the debate over planets impossible to postpone. Eris showed that large worlds could remain hidden at immense distances for a very long time. Before it was recognized, it had continued along its orbit for billions of years, reflecting a faint amount of sunlight toward Earth without anyone realizing that the light came from a body nearly the size of Pluto. Eris has a moon named Dysnomia. By tracking the motion of this moon, scientists were able to calculate the mass of Eris. It is a remarkably subtle way to measure a world we have never seen clearly. Eris pulls on its moon through gravity, while the moon's orbit reveals the strength of that pull. From the motion of one tiny point of light around another, the mass of an entire distant world can gradually be determined. Not every object, however, has a moon that is easy to observe. For many bodies beyond Neptune, measuring size remains a challenge. A brighter point of light is not necessarily larger, because brightness also depends on the surface. A small world covered in reflective ice may shine more strongly than a much larger object with a dark surface. This means that some large bodies may still not have been recognized at their true size. They may already appear in the data as faint points of light, while their dark surfaces make them seem smaller than they really are. Others may currently lie near the most distant part of an elongated orbit, where the reflected sunlight is too weak for older surveys to detect. The list of dwarf planets beyond Neptune is therefore probably still incomplete. We know of several worlds large enough to be nearly round, along with many candidates whose dimensions have not yet been measured precisely. There may still be bodies, hundreds or even more than 1,000 kilometers across, carrying moons, distinctive layers of ice, and histories that have never been observed. There is no need to assume that a giant planet is hiding just beyond Pluto to understand how much remains unknown in this region. Even a few large, dark worlds that have not yet been recognized could significantly change the way we picture the population of the outer solar system. Sometimes, to measure such an object, astronomers must wait for it to pass in front of a distant star. For a few brief seconds, the star's light dims or disappears. The duration of the event reveals the object's width, while the way the light fades may offer clues about its shape or the presence of an extremely thin atmosphere. It is a method well suited to the outer solar system, where most worlds do not allow us to see their surfaces directly. Instead, they are detected through the faintest effects: a point of light shifting position, a small moon changing place, a darkened region in a spectrum, or the light of a star vanishing for a moment. Each sign reveals only a very small part of the whole. But when these clues are combined, they are enough for a distant world to gradually acquire its own size, mass, and place on the map. Pluto once stood at the edge of that map as an exception. Today, it stands within a much larger population, where some bodies are only small masses of ice, while others have come remarkably close to the complexity of a planet. Names may change as understanding expands, but the nature of these worlds does not depend on human language. Pluto remains Pluto, with its long seasons, frozen plains, and thin atmosphere. Eris continues along its elongated orbit through the deep cold. Unknown bodies still move through the darkness, even though they have no names or positions on any map. Perhaps the most important lesson left by the story of classification is not which word should be used for Pluto. What matters more is that whenever we believe we understand the structure of the solar system, another world appears and forces the map to grow. Pluto did not lose a title and become smaller. It simply no longer had to stand alone. And when the light of a distant star suddenly dims for a few seconds, another member of that family may have just passed in front of it, casting its first shadow across Earth. Some worlds beyond Pluto are too small and too distant for telescopes to resolve their outlines. In images, they remain only faint points of light among thousands of stars. Yet every so often, an object's orbit carries it directly in front of a more distant star. The steady light suddenly dims, disappears for a few seconds, and then returns as though nothing had happened. This brief event is known as a stellar occultation. Nothing changes for the star in the background. It continues shining as before. A small world within our solar system has simply crossed the line of sight from Earth, blocking some of the light and allowing its shadow to sweep across our planet. During ordinary observations, astronomers must rely on the tiny amount of sunlight reflected by the object itself. The farther away, smaller, or darker a body is, the harder it becomes to detect. But during an occultation, the background star serves as a natural source of illumination. The object does not need to be bright. It only needs to pass through the right position, and the amount of starlight it blocks reveals how much space it occupies. To observe such an event, scientists must predict in advance where the shadow will cross Earth. This is not easy, because a very small error in the position of either the object or the star can shift the shadow path by hundreds of kilometers. For that reason, multiple telescopes are often arranged along the region where the shadow is expected to pass. Some are located at major observatories, while smaller instruments may be carried far from cities to places where the sky is dark and the horizon is open. When the event begins, each telescope sees something slightly different. A location near the center of the shadow path will see the star disappear for a longer time. A site near the edge will record only a brief interruption. A telescope outside the shadow will detect no change at all. When observations from many locations are combined, scientists can reconstruct the outline of the object, much like assembling several cross-sections into a complete shape. This method is especially useful because brightness does not always reveal true size. A small object covered in reflective ice may shine more brightly than a larger body with a dark surface. If brightness alone is considered, two very different worlds can sometimes appear almost the same. A shadow, however, does not depend on color. It directly reflects the width of the object blocking the star. In this way, a world with no clear photograph can still be measured with remarkable precision. But size is not the only information hidden in the way starlight disappears. Sometimes the more interesting clues are found in the seconds just before the star is completely blocked. Pluto once revealed its atmosphere in this way. Before New Horizons arrived, humanity had no clear images of the thin haze surrounding Pluto. Yet when this world passed in front of a star, the light did not vanish instantly at the edge. It faded gradually, as though sinking through a very thin layer of gas before Pluto's solid body blocked it completely. On the other side, the light did not return all at once. It gradually brightened again after passing through the upper layers of gas above the surface. From this pattern of dimming and brightening alone, astronomers learned that Pluto was not a bare sphere of ice. An atmosphere surrounded it, far thinner than Earth's, yet still dense enough to bend and absorb some of the starlight. Occultations observed in different years also helped scientists track changes in that atmosphere. Pluto travels around the Sun on an orbit lasting nearly 250 years. As its distance changes, surface temperatures also shift slightly. Some nitrogen ice can turn into gas as Pluto warms, then freeze again as the world moves farther from the Sun and grows colder. The seasons there last for many decades, far too long for one human lifetime to follow in full. Yet each time a star passes behind Pluto, it provides a brief measurement of the atmosphere at one moment within that extended season. Through these scattered events, humanity gradually learned that even a world so distant and cold is not completely still. After the starlight returns, Pluto simply continues along its orbit. Nothing on Earth's surface reveals that an atmosphere billions of kilometers away has just been measured. Only within the data has the light changed enough for an invisible layer of gas to emerge. But sometimes an occultation reveals something astronomers were not expecting at all. Haumea is a world smaller than Pluto, rotating very rapidly and stretched into an elongated shape. Before 2017, scientists already knew that it had a surface rich in water, ice, and several moons. But when Haumea passed in front of a star, the light produced an unusual sequence of changes. Just before Haumea's main body blocked the star, the brightness dipped slightly for a very brief moment. After the body had passed and the starlight returned, a similar dip appeared on the opposite side. The two small signals were almost symmetrical, indicating that a thin structure surrounded Haumea. It was a ring. At the time, no telescope on Earth could photograph this ring as a visible band like those surrounding Saturn. It was too small, too dark, and far too distant. But as it crossed the light of the background star, the material in the ring left two brief signals on either side of Haumea's main body. A structure never seen directly appeared in the data, simply because it blocked the light at the right moment. This discovery showed that rings do not belong only to the giant planets. A much smaller body in the cold region beyond Neptune can also be surrounded by orbiting material. The origin of Haumea's ring is still being studied. It may be connected to a collision in the past, or to fragments once separated from Haumea and later retained around it. More importantly, the region beyond Pluto once again proved to be unlike the simple image people had first imagined. It contains more than isolated blocks of ice following separate orbits. Some worlds have atmospheres. Some have moons. Others are surrounded by rings so faint that they appear only when passing across the light of a star. Pluto and Haumea left two different kinds of traces. Around Pluto, the light faded gradually as it passed through the atmosphere. Around Haumea, the star flickered several times because a ring extended beyond the surface. The same observational method allowed each world to reveal something entirely its own. Not every occultation is successful. Sometimes the shadow misses the telescopes that have been prepared. Sometimes clouds arrive just as the event begins. On other occasions, only one location records the star disappearing, leaving the object's shape uncertain. A moment lasting only a few seconds may require months of calculation, preparation, and waiting. This method cannot be used for every object beyond Pluto. From Earth's point of view, the body must pass almost exactly in front of a star bright enough to observe. Of the millions of worlds that may exist in the outer solar system, most will not produce a favorable event during the time humanity is able to watch them. The shadows we have seen are therefore only a very small fraction of the whole. Many bodies out there have never passed in front of a star while human telescopes were watching. They have not revealed their true size, shown whether they possess an atmosphere, or produced the subtle signals that might uncover a moon or a ring of orbiting material. They continue moving along orbits that last for centuries, while astronomers on Earth patiently follow distant points of light and wait for a rare moment of alignment. Then a star disappears. A shadow sweeps across a small region of Earth, lasting only long enough for instruments to record a few lines of data. The light then returns, while the world in front of it continues on its distant path, leaving almost no other trace behind. Yet from those few brief seconds, a body that was once only a point of light acquires a width and an outline. It may reveal an atmosphere or a ring turning silently in the darkness. Each shadow helps humanity understand one individual world more clearly. But to answer the larger question, how many objects truly exist beyond Pluto? We must move beyond these rare moments and turn to broader surveys, where thousands of points of light are gathered so that science can use the portion already seen to estimate everything that still remains hidden. Stellar occultations allow astronomers to measure the sizes of a few individual worlds, but they cannot answer the broader question waiting beyond them. If most objects beyond Pluto have never passed in front of a sufficiently bright star, have never been approached by a spacecraft, and have not even appeared clearly in any image, how can science say that millions of bodies exist out there? The answer does not come from seeing every world one by one, but from learning what the portion we have seen represents. A telescope can observe only a limited area of sky. During each survey, it is pointed toward a region selected in advance, records the points of light within it, and then returns after a period of time to search for anything that has changed position. The distant stars remain almost fixed, while an object within the solar system shifts slightly against the background because it is orbiting the Sun and because Earth itself is also moving. Among the thousands or millions of points of light in each image, computers identify candidates whose motion fits the expected pattern. Astronomers then conduct further observations to confirm that these are truly objects beyond Neptune rather than detector noise, nearby asteroids, or signals that appeared in the data by chance. Every new discovery adds another point to the map, but the number of points found is never the full population of the outer region. Some bodies are large and bright enough to appear in the earliest surveys, while smaller, darker objects, or those currently near the most distant part of their orbits, may leave no detectable trace at all. Before scientists can use the number of discoveries to estimate how many objects remain hidden, they must first understand how far their survey is capable of seeing. Every telescope has a brightness limit. Sources brighter than that limit are usually detected with relative ease, but as the light grows fainter, the likelihood of detection begins to fall. An object may be present in an image without standing out clearly enough for the system to separate it from the background. Near the faintest limit, only a small fraction of the real objects may be found, while the rest remain in the data without ever being confirmed. To measure this limit, researchers can insert artificial points of light into the images, give them different brightness levels and rates of motion, and then test how many the search program is able to recover. If nearly every artificial source at a certain brightness is detected, the survey is considered highly effective at that level. As the sources become dimmer and more of them begin to escape detection, scientists know they are approaching the range where the data no longer provide a complete picture of the true population. In this way, a discovery is more than a single object added to a list. It also represents similar bodies that the survey may have missed. Suppose a survey finds 10 objects at a certain brightness, while testing shows that the instruments detect only about half of all bodies at that level. Those 10 discoveries are no longer understood as the entire population within the observed region, but as evidence that the true number may be closer to twice as many. If the detection efficiency falls to only 1 in 10, each object that is seen may represent many others that remain below the observational limit. This process of inference is not a perfect measurement, because a world's brightness depends on more than its size. A surface covered in reflective ice may make a small object appear unusually bright, while a larger body with a dark surface may be so faint that its size is underestimated. Distance changes everything as well, because the same object will appear brighter when it moves closer to the sun and far dimmer when it reaches the distant portion of its orbit. Astronomers must therefore combine many different factors. They measure brightness, estimate reflectivity, use thermal data to determine size whenever possible, and account for the shape and inclination of each orbit. From many surveys, each with its own limits, a statistical picture gradually begins to emerge. That picture does not reveal the name and position of every world, but it can show how numerous the population may be within each range of sizes. Large objects are rarer, while their numbers generally increase as their size decreases. This is a natural pattern for a region shaped by both formation and collision. Only a small number of bodies accumulated enough material to become large worlds, such as Pluto or Eris, while most of the population exists as far smaller masses of ice. When scientists say that the region beyond Neptune may contain millions of worlds, they do not mean that millions of dwarf planets or millions of Earth-like places are waiting there. Most may be only a few kilometers across, some even smaller, and many have irregular shapes because their gravity is not strong enough to pull their material into a nearly round form. Yet their small size does not make them insignificant. Each object still has its own orbit, composition, age, and history. Some may be ancient masses of material that have never undergone profound change. Others may be fragments left by collisions that occurred long ago. Some could become comets if their orbits were altered and carried them closer to the sun. Their numbers also help science read the history of the Kuiper Belt. If the population contains many objects within one size range but fewer than expected within another, that difference may reveal how the original formation process unfolded. The earliest bodies may have grown gradually from smaller particles, or some larger objects may have formed more quickly when material in the disk surrounding the young sun became concentrated in dense regions. Different models predict different populations. Some produce many small bodies, while others form a larger number of substantial objects from the beginning, and the later history of collisions continues to alter the balance between them. When surveys measure the true distribution, scientists can compare it with these different scenarios and eliminate explanations that do not fit the evidence. Counting the worlds beyond Pluto is therefore not simply an attempt to produce an impressive number. The shape of the entire population, from the largest dwarf planets to the small icy bodies that have never been seen, is a surviving trace of the era when the solar system was still taking form. To build that picture, astronomers must balance two different approaches to observation. A wide survey can cover a large portion of the sky, but it will find only relatively bright objects. A telescope looking much more deeply can detect far fainter points of light, but only within a small region. Wide surveys reveal where objects are distributed, while deep surveys show how quickly their numbers increase as telescopes reach fainter levels of brightness. When these two kinds of data are combined, part of the invisible population begins to take shape, not as a complete map, but as patterns of density, size, and probability. We might imagine standing inside an enormous room with only a narrow beam of light falling across the floor. Within that illuminated strip, some grains of dust become clearly visible. Smaller particles appear only when the light grows stronger or when we look more closely. From the number seen at each level, we can infer that the room contains far more dust than our eyes can directly detect. The important thing is to understand the beam itself. Unless we know how wide it is, how bright it is, and the size at which particles begin to disappear from view, any estimate of the entire room would be little more than a guess. The science of the Kuiper Belt works with this same caution. Astronomers do not claim to know the exact location of every object. Instead, they provide a range of estimates based on the available data and the limitations of their instruments. When a new telescope begins operating or a deeper survey is completed, those numbers may be revised. Such changes do not mean that earlier estimates were worthless. They show that the map is gradually becoming more complete, much as a coastline grows clearer when observers add measurements from regions that were once left uncharted. By now, our journey has carried us far enough to look back at the original question. Pluto was once regarded as the final world, but then other points of light began appearing beyond Neptune. Their orbits showed that they were not arranged within a simple ring, while reflected light revealed surfaces that were anything but identical. Some were large enough to possess atmospheres, moons, or rings of material. Stellar occultations allowed individual worlds to be measured, while broader surveys showed that every discovery represented only a small part of the true population. The question is no longer whether anything exists beyond Pluto. That was answered long ago. The deeper question is how much of what exists has actually been seen. And the answer, for now, is still only a very small fraction. Large and bright objects are more likely to be discovered first. Smaller, darker bodies, or those following more steeply inclined orbits, are still easily missed. Some areas of the sky have been observed many times, while others have never been surveyed deeply enough. Even within data already collected, certain worlds may still lie below the threshold of recognition, appearing only as points of light too faint to be separated from the background stars. Millions of objects may continue moving through the distant region without ever entering a catalog. They have no names, no photographs, and many may remain undiscovered for a very long time. Even so, the presence of the wider population can be recognized in the way the numbers continue to rise whenever telescopes look more deeply. Each new limit that is crossed reveals more points of light, as though the darkness were never empty, but merely waiting for an instrument sensitive enough to uncover what had always been there. Yet even the most densely populated part of the Kuiper Belt is not the whole outer solar system. Some objects no longer follow relatively stable orbits near Pluto. Neptune has pushed them farther away, sending them along elongated paths that may take thousands of years to return to the region closer to the Sun. Beyond the familiar portion of the belt, the population gradually becomes thinner, but its orbits extend across far greater distances. This is the realm of the scattered disk, where small worlds preserve some of the clearest traces of an age when Neptune disturbed the entire outer solar system. And there, the boundary of the map begins to retreat once more. As we leave the more densely populated part of the Kuiper Belt, we do not encounter a clear boundary where every object suddenly disappears. Instead, the map gradually grows thinner. The distances between bodies widen, and orbits that once seemed relatively orderly begin stretching in many different directions. Some worlds continue circling the Sun at distances not vastly different from Pluto's, while others pass through that region for only a brief part of their journey before traveling billions of kilometers farther outward. This broad and difficult to define realm is commonly called the scattered disk, a name that describes not only where these objects are found, but also the history that carried them away from their original, more stable orbits. An object in the classical Kuiper Belt usually remains within a relatively consistent range of distances from the Sun, although its orbit may still be tilted or slightly elongated. Bodies in the scattered disk move very differently. The distance between the nearest and farthest points of their orbits can be enormous. causing the same world to spend part of its journey within reach of telescopes and another part so deep in the darkness that its reflected light nearly disappears. A single revolution around the sun may last hundreds or thousands of years, and for most of that time, the object may remain far more distant than it was when humanity first detected it. This creates a particular challenge for observation. A world may be discovered while approaching the closest point in its orbit, where it receives more sunlight and reflects a signal strong enough to reach Earth. As it moves outward again, its brightness falls rapidly. Not because the object itself has changed, but because sunlight must travel farther to reach its surface and then make the long journey back to our telescopes. If that same body were currently near the most distant part of its orbit, it might lie beyond the reach of many surveys. What we see in the scattered disk is therefore only the portion of the population that happens to occupy more favorable positions during journeys far longer than the entire history of human observation. The origins of these vast orbits are closely connected to Neptune. Early in the history of the solar system, this giant planet probably did not remain fixed at its present location. Instead, it gradually migrated outward while interacting with a disk of material far more crowded than the region is today. At that time, countless bodies of ice and rock surrounded it, none of them yet incorporated into planets, all moving within a system that had not fully settled. Whenever a small object passed close enough to Neptune, the planet's gravity could alter both its speed and direction. No direct collision was necessary. A single well-placed encounter could transform a relatively circular orbit into one that was longer, more steeply tilted, and extended far into the outer solar system. Not every object that encountered Neptune experienced the same outcome. Some were captured in stable orbital resonances, where their rhythms became linked to the planet in ways that helped them avoid dangerous close approaches. Pluto is the most familiar example of this arrangement. Other bodies gained enough energy to be pushed farther outward, but not enough to escape the sun entirely. They remained in orbit around the central star, although their new paths became far wider than before. Over millions of years, some continued to encounter the giant planets and underwent further changes, while others remained on elongated orbits that have altered very little during most of the solar system's lifetime. The process can be imagined as a great current redirecting smaller objects carried within it. Neptune never needed to touch each body, yet its gravity was strong enough to bend their paths, exchange energy with them, and carry them into regions they had never occupied before. For a giant planet, each individual interaction may have produced only a slight change, but for a body of ice with vastly less mass, the effect could define the entire remainder of its orbit. The scattered disk is therefore more than a region located beyond the Kuiper Belt. It is what remains of a vast rearrangement during which the giant planets transformed the structure of the outer solar system. The orbits in this region are not all stable in the same way. Some objects still return close enough to Neptune for the planet to influence them again in the future. After each encounter, their paths may change a little more, even though the difference would appear almost imperceptible within a human lifetime. Across millions of years, these accumulated changes can push a body farther outward, carry it into the region among the giant planets, or even eject it from the solar system. The pace of change is so slow that everything appears nearly motionless from Earth, but on the timescale of the solar system, the scattered disk remains a dynamic realm capable of continuing to rearrange itself. Some objects from this region may begin a journey back toward the sun. As their orbits change, they can enter the space among the giant planets, where the gravity of Neptune, Uranus, Saturn, and Jupiter continues to redirect them. Such bodies are often classified as centaurs, a population with relatively unstable orbits and dynamical lifetimes much shorter than those of objects remaining in the distant regions. After repeated gravitational encounters, some may travel deeper into the solar system, where rising temperatures cause surface ices to turn into gas, carrying dust with them and creating the familiar haze and tail of a comet. Seen this way, a comet appearing near Earth may have spent most of its history beyond Neptune, resting in darkness for billions of years before its orbit changed. The brief period when it brightens near the sun represents only a tiny fraction of its entire journey. Before becoming a tailed object in the sky, it may have been a small, frozen, nearly inactive world moving through the scattered disk on an elongated orbit. This means the outer region is not completely separated from the domains closer to the sun. Slow, dynamical pathways connect them, allowing bodies to travel from distant darkness back into stronger light. Most objects in the scattered disk, however, will not become comets on any timescale meaningful to human life. They continue circling the sun on immense paths, passing through seasons that last for centuries and spending most of their time at distances where temperatures fall extremely low. If we could stand on one of these worlds, the sun would still be the brightest object in the sky, but it would appear far smaller than it does from Earth. Its light would still cast shadows and keep the body in orbit, yet it would offer no sense of warmth. The surface would change mainly through radiation, rare collisions, and very slow thermal cycles as the distance from the sun gradually shifted. The scientific value of these worlds does not depend on whether they might ever approach Earth. Their orbits themselves preserve evidence from the age when the giant planets were still migrating and the outer solar system had not yet become stable. If Neptune had moved outward at a different rate, begun from another location, or encountered a disk with a different amount of mass, the population remaining today would have a different structure. By measuring the inclinations, elongations, and distances of many orbits, then comparing them with computer simulations, scientists can identify the scenarios that most closely match the true history of the solar system. Eris is a striking example of a large world whose orbit is associated with this scattered realm. It does not remain near Pluto's distance, but travels along a broad and steeply inclined path that at times carries it much farther from the sun. Its large size and fairly reflective surface make Eris detectable even at such distances, but smaller objects on similar orbits would be far fainter, especially when approaching their most distant points. This makes estimating the population of the scattered disk more difficult than estimating that of the main Kuiper Belt, because its objects are not only spread across a vast region of sky, but also spend most of their time at distances that are unfavorable for observation. A sparse-looking map of the scattered disk does not necessarily mean that the region truly contains very few objects. Each discovered world may represent many similar bodies currently located in more distant parts of their orbits or covered by darker surfaces. Before estimating the true population, surveys must account for how long each object spends at different distances, how steeply its orbit is tilted, and how faint a telescope can see. The estimates still carry considerable uncertainty, but they all show that the outer solar system does not end just beyond the most densely populated part of the Kuiper Belt. It continues outward along immensely elongated orbits, where small worlds are distributed across a region far greater than the familiar belt itself. At this point, the idea of an edge to the solar system becomes difficult to define once again. The Kuiper Belt does not end at a wall, and the scattered disk has no boundary where every orbit suddenly stops. The different populations blend into one another, and the distinction often lies more in their histories of motion than in their positions at any particular moment. Some objects remain clearly influenced by Neptune because their orbits continue to carry them back toward the planet, while other worlds never come close enough for Neptune to keep shaping their paths in such a direct way. These detached objects open the next layer of the outer solar system. If a body follows an extremely elongated orbit but never approaches Neptune, then the giant planet is unlikely to be the only cause of its present path. Scientists must then consider more ancient influences, perhaps from the time when the sun still belonged to the star cluster in which it was born, or from an encounter with another star that once passed close enough to disturb the most distant orbits. These possibilities are not yet certain explanations, but they show that the farther we travel beyond Pluto, the more each newly discovered world does more than expand the map. It also raises questions about the earliest chapters of the solar system. The scattered disk is therefore a realm of bodies that have left their original formation region without escaping the Sun. They move along vast orbits, carrying traces of Neptune and of an age when the giant planets were still rearranging the outer solar system. Farther beyond lie worlds that appear to have become detached from Neptune's direct influence, where a single journey around the Sun may last many thousands of years, and the origins of their orbits remain an open question. From here, our journey will continue deeper into the darkness, toward objects that were not merely scattered outward, but now remain so far from Neptune that their paths seem to have been written by a different gravitational influence. One that appeared during an early chapter the solar system has not yet fully revealed. Within the scattered disk, many objects still carry the clear signature of Neptune, because their elongated orbits eventually bring them close enough for the planet's gravity to continue altering their paths. But as surveys reached deeper into the outer solar system, other bodies began to appear on orbits that were more difficult to explain. They travel very far from the Sun, yet even at their closest point, they never enter the region where Neptune could easily have pushed them onto their present trajectories. Worlds like these are often called detached objects because their orbits appear to have separated from the direct control of the outermost giant planet. The difference does not lie in where an object happens to appear in a single image, but in the full path it follows around the Sun. A scattered disk object may currently be extremely distant, yet the nearest point in its orbit still brings it back toward Neptune's neighborhood, where encounters in the past or future may continue to reshape its motion. For a detached object, even the portion of its orbit closest to the Sun lies too far away for an ordinary encounter with Neptune to fully explain the shape of its path. That distance creates a kind of gravitational separation, leaving the body bound to the Sun while no longer participating directly in the pattern of interactions that produced most of the scattered disk. Sedna is the most famous world in this group. When it was discovered early in the 21st century, it appeared as an extraordinarily slow-moving point of light against the stars, its slight motion revealing that it lay at a tremendous distance. Follow-up observations gradually established an orbit so unusual that even Sedna's closest approach to the Sun remains more than twice Neptune's average distance from it. From there, the orbit extends across such an enormous region that Sedna requires more than 10,000 years to complete a single revolution, spending most of that time too far away for present-day telescopes to easily detect a similar object. If the orbits of the familiar planets were reduced to scale on a diagram, Sedna's path would be almost impossible to fit within the same frame while preserving the proportions. Neptune circles the Sun at about 30 astronomical units, with 1 astronomical unit representing the average distance between Earth and the Sun. Sedna never comes anywhere near that close. At its nearest point, it remains more than 70 astronomical units from the Sun, then travels hundreds of astronomical units farther outward before slowly returning. During one orbit of Sedna, the entire recorded history of many civilizations on Earth would occupy only a relatively small portion of its journey. Because its orbit is so long, the timing of Sedna's discovery involved a considerable degree of luck. The object is currently in the nearer part of its path, where sunlight, although already extremely weak, is still strong enough for the surface to reflect a detectable signal. If Sedna were near the farthest point in its orbit, its brightness would fall dramatically, and finding it through similar surveys might become almost impossible. This also suggests that Sedna may not be entirely alone, because other worlds following comparable paths could be spending thousands of years in regions too dark to appear in present-day data. Sedna's surface has a deep red color, a feature seen on some objects beyond Neptune after carbon-rich compounds have been altered by radiation over immense periods of time. Thermal measurements suggest that Sedna is nearly 1,000 kilometers across, making it a substantial world, though still smaller than Pluto. At such a great distance, the surface temperature is extremely low, and most volatile substances remain frozen, leaving the body with little obvious activity through most of its orbit. Yet Sedna's greatest importance lies not in its appearance or size, but in a path that seems impossible to create through familiar interactions with Neptune alone. If Sedna formed closer to the region of the planets, some force must have carried it onto its present expansive orbit, while also raising its closest point far enough to prevent it from returning to Neptune. A giant planet can push an object outward relatively easily, but separating the entire orbit from the planetary region requires another process. Neptune may stretch a body's orbit, but without an additional influence, the nearest point usually remains within the region where the planet can continue affecting it. Sedna, therefore, resembles a world that was driven outward and then lifted away from the path that would have brought it back, leaving it to continue along a broad and relatively stable orbit. One possibility carries us back to the Sun's earliest years, when it may not yet have been traveling alone through the Milky Way as it does today, but still belonged to a cluster of stars born from the same cloud of material. In that environment, the distances between stars would have been smaller than they are around the Sun now, allowing another star to pass close enough to alter the orbits of the most distant bodies. The gravity of that ancient encounter would not have needed to pull Sedna away from the Sun. It would only have needed to disturb the outer part of its orbit, raise its closest approach, and leave the body on a path that the present-day planets would struggle to produce. If this scenario is correct, Sedna is more than a distant object. It is a trace of the environment in which the Sun was born. Planets and asteroids closer to the Sun have experienced repeated collisions, thermal changes, and gravitational disturbances, erasing much of the information about that original star cluster. Farther out, some orbits may still preserve the influence of encounters that took place more than 4 billion years ago. The present path of a small world could then become surviving evidence of stars that once passed near the Sun before dispersing long ago through the wider motion of the Milky Way. Another possibility involves influences that act more slowly across enormous distances. When a body travels hundreds or thousands of astronomical units from the Sun, the gravity holding it in orbit becomes weaker, and forces that seem insignificant within the planetary region have far more time to accumulate. The overall gravitational field of the Milky Way, along with distant stellar passages, can gradually alter the orbits of the outermost bodies. These effects are especially important for the far more distant Oort Cloud, but in some models of the early solar system, they may also have helped create or preserve orbits lying between the scattered disk and that remote Oort region. The boundaries between these regions are not entirely clear, because nature does not arrange objects into the categories created by human beings. Sedna is sometimes called a detached object, sometimes considered a member of the inner Oort Cloud, while more cautious classifications place it within a small group of bodies whose closest approaches to the Sun are unusually distant. Each name emphasizes a different part of the problem, but all reflect the same reality. Sedna lies beyond the familiar Kuiper Belt, yet not far enough away to be considered a typical member of the Oort Cloud. Since Sedna's discovery, several other objects with distant orbits and large perihelion distances have been found, including 2012 VP113. The number currently known remains very small, not necessarily because such worlds are rare, but because they are extraordinarily difficult to detect. Their vast orbits keep them far away for most of the time. Their apparent motion across the sky is extremely slow, and they reflect too little light to stand out in shallow surveys. Finding them requires deep images, a sufficiently broad field of view, and the right interval between observations to recognize a point of light that has shifted only slightly among countless background stars. Their small known number also makes it difficult to draw conclusions about the population as a whole. When only a few objects have been identified, similarities among their orbits may be evidence of a real physical process, but they may also arise from the way surveys select particular regions of the sky. Telescopes do not observe every direction to the same depth, and the easiest objects to detect are usually concentrated near the portions of their orbits closest to the Sun. Unless these biases are carefully accounted for, a small group of orbits may create the impression of an order that the full population does not actually possess. This is where science must maintain a careful distance between what has been observed and what remains hypothetical. These distant orbits show that part of the outer solar system's history has not yet been fully explained, but they do not point by themselves to a single cause. A stellar encounter within the Sun's birth cluster may have created some of these paths. The evolution of the giant planets may have contributed other effects, while extremely slow influences from the galactic environment may have continued reshaping the distant region over billions of years. Several processes may also have acted together, leaving behind a history more complex than any single explanation. Beyond these possibilities connected to the past, another idea often appears when astronomers examine the orbits of detached objects. If a large body is still moving through the distant outer solar system but has not yet been detected, its gravity could influence smaller worlds and help organize their orbits. This idea did not begin with an image of a newly discovered planet, but with the question of whether these remote paths might carry the signature of an unseen source of gravity. However, an undiscovered planet is not the only possible explanation, and its existence cannot yet be regarded as confirmed. Too few detached objects are currently known, the orbits of some bodies have not been measured for long enough, and observational biases may still exert a strong influence on the pattern we see today. To test the idea, scientists need to find many more worlds like Sedna, determine their orbits more precisely, and see whether the apparent patterns remain once the data become more complete. This is also why new surveys matter for more than simply adding names to a catalog. Every newly discovered detached object provides another test of hypotheses involving the Sun's early star cluster, the migration of the giant planets, and the possible existence of a more distant source of gravity. If the orbits prove randomly distributed after observational biases are removed, some ideas will become less convincing. If they continue to cluster around particular directions or distances, science will need to identify a mechanism powerful enough to preserve that structure for billions of years. As the searches continue, Sedna is still moving slowly through the nearer portion of its orbit, although nearer here remains far beyond Neptune. No spacecraft has ever visited it, and through telescopes, the object is still only a tiny point of light, revealing no mountains, plains, or changes across its surface. Yet its orbit has opened an entirely new region in the human picture of the solar system, one where the influence of the familiar planets is no longer enough to explain every motion. Farther inward, Neptune once scattered countless worlds and created the elongated orbits of the scattered disk. Farther outward, Sedna and a few other rare bodies appear to have traveled so far that they no longer return to that region of direct influence. Between these two realms lies a broad transition zone, where the history of the solar system may have been written by migrating planets, passing stars, and gravitational forces acting across spans of time longer than the entire history of humanity. Detached worlds do not mark a final edge, because their orbits have carried us only into the beginning of an even more distant realm, yet they change the question guiding this journey. After learning that millions of objects exist beyond Pluto, we begin to recognize that some of their orbits may be pointing toward something never directly seen, an influence distant enough to remain hidden from surveys, yet strong enough to leave traces in the motion of small worlds. The hypothesis of a large, unseen source of gravity has therefore become one of the most debated areas of research in the outer solar system. Some models suggest that it could explain orbital features seen in distant bodies, such as Sedna, while other analyses argue that the apparent patterns may still arise from limited data or from known dynamical processes. Evaluating these possibilities will require many more observations and more precise data from objects moving through the farthest reaches of the solar system. The Planet 9 hypothesis did not begin with a new point of light appearing in a telescope, but with the way certain small worlds beyond Neptune move. When the orbits of Sedna and other distant objects were compared, astronomers noticed that some of their paths did not seem to be distributed entirely at random. The directions in which they approached the Sun, the tilts of their orbital planes, and the orientations of their ellipses in space showed notable similarities, as though these extremely distant bodies were responding to a shared gravitational order that the 8 known planets could not fully explain. From this unusual pattern, a specific hypothesis was proposed in 2016. A large planet that has never been directly observed might exist in the dark region far beyond Pluto. This hypothetical world became known as Planet 9, not because it had been officially recognized as the 9th member of the solar system, but because, if it exists, it would be a planet of substantial mass orbiting beyond Neptune. So far, no image or measurement has directly confirmed its presence. Every description of its mass, orbit, and location, therefore, comes from dynamical models rather than observed characteristics. The central idea is somewhat similar to the way Neptune was inferred before it was seen. A large world may not appear clearly through a telescope, but its gravity can still influence other objects. If several small bodies repeatedly follow orbits that share certain features, a more distant source of gravity may be helping preserve that structure over long periods of time. The challenge is not to explain one unusual object, but to understand why a group of extremely broad orbits has not been completely dispersed by other interactions over billions of years. In simulations that support this hypothesis, Planet 9 does not pull distant objects into a fixed line or force them to travel along the same path. The gravity of a planet at such a great distance would act more slowly and subtly. Over millions of years, it could cause the orientations of their orbits to oscillate around certain positions, preventing them from becoming entirely random. This process is sometimes described as gravitational shepherding, in which each body continues along its own orbit while the long-term motion of the group is influenced by the same distant source. A sufficiently massive planet could also help raise the closest points of some orbits farther from the Sun, creating detached paths like Sedna's. In other simulations, it may be able to lift certain bodies onto highly inclined orbital planes, some nearly perpendicular to the plane in which the 8 major planets move. The appeal of the hypothesis lies in the possibility that a single world could connect several seemingly unrelated features of the outer solar system, rather than requiring a separate explanation for every type of orbit. Based on the strength of the influence required, modern models often imagine Planet 9 as several times more massive than Earth, yet still far less massive than Neptune. If it exists, it could represent a type of world with no counterpart among the 8 known planets, larger than rocky planets such as Earth, but smaller than an ice giant. Planets within this range of mass are fairly common around other stars, while our own solar system appears to lack a world between Earth and Neptune. The predicted orbit of Planet 9 would be far wider than Pluto's, with an average distance possibly reaching several hundred times the distance between Earth and the Sun. One complete revolution could last thousands of years, making the planet's true movement against the background stars extraordinarily slow. Its distance from the Sun may also change greatly over the course of its orbit. If it is currently near its farthest point, it would receive and reflect far less sunlight than it would closer to the Sun. At such a distance, even a large planet would not appear as a round disk. It would be only a faint point of light among countless background stars and galaxies. Sunlight would need to travel tens of billions of kilometers to reach the planet's surface, after which only a tiny fraction would be reflected back toward Earth. If the surface is dark, or if the planet lies farther away than expected, its signal may be weak enough to fall below the limits of earlier surveys. The search is made even more difficult because the models do not provide a single coordinate. The predicted orbit is inferred from a small group of objects and still contains considerable uncertainty, leaving Planet 9 potentially hidden across a broad region of sky. Telescopes must photograph the same areas at different times and then search for a point of light moving extremely slowly through a dense background of other sources. Near the Milky Way, where millions of stars crowd into the same field of view, separating a dim, slow-moving planet from the background becomes especially difficult. Many surveys have searched regions where Planet 9 might be located without finding a convincing candidate. These non-detections still have value because they gradually eliminate positions and brightness levels where the planet cannot be hiding. Over time, the remaining regions consistent with the models have narrowed, often toward areas that are difficult to observe or distances where the planet could be fainter than expected. Yet failing to find it in the regions already surveyed does not completely rule out the hypothesis, because some areas have still not been examined deeply enough. A greater difficulty lies within the evidence that inspired the hypothesis in the first place. Distant objects are not discovered evenly across the entire sky. Telescopes often avoid regions crowded with stars, weather, and observatory location limit which areas can be monitored, and an object may become bright enough to detect only when it is near the closest point of its orbit. These biases can cause certain orbital directions to appear more often in the discovery record, even if the true population is distributed more evenly. Some research groups argue that once the way surveys selected their observing regions is taken into account, the apparent orbital clustering is no longer strong enough to require a new planet. Other analyses conclude that observational bias cannot fully explain the structure, and that simulations containing Planet 9 still fit the data more closely. These two interpretations have not yet fully converged, mainly because the number of extremely distant objects with well-determined orbits remains far too small. A discovery announced in 2025 made the picture even more complicated. The object 2023 KQ-14, nicknamed Ammonite, follows a stable orbit whose closest point to the Sun lies far beyond Neptune, placing it within the broader group of Sedna-like worlds. Yet the present orientation of its orbit does not align with the three similar objects known before it. That difference weakens the simplest interpretation that all detached worlds are being guided in the same way by one distant planet. Ammonite does not prove by itself that Planet 9 does not exist, because its orbit may occupy a transitional region influenced differently from objects farther away. Simulations also suggest that if a large planet is present, it may need to follow a more distant orbit or possess different characteristics from some earlier predictions. Even so, this discovery is a reminder that each new object does not necessarily strengthen the existing picture. Sometimes it forces scientists to expand or revise the hypothesis. There are also other ways to produce such distant orbits besides a planet that still exists today. A passing star, encountered while the Sun was still inside its birth cluster, may have raised the closest approaches of Sedna and similar objects. A planet that existed early in the solar system and was later ejected could also have left traces before disappearing. The migration of the giant planets, together with extremely slow influences from the galactic environment, may have helped create a population more varied than any single model can explain. The question of Planet 9, therefore, cannot be reduced to two simple answers. Either it exists or it does not. If it is found, scientists will still need to explain where it formed, how it reached such a vast orbit, and why it was not expelled from the solar system. If sufficiently deep surveys eventually rule out every plausible orbital region without finding the planet, the strange paths that inspired the hypothesis will not disappear. They will still need to be explained through the Sun's early history, or through mechanisms that are not yet fully understood. A world several times more massive than Earth would have difficulty forming directly hundreds of astronomical units from the Sun, where the original disk of material was too thin and too cold for rapid growth. If Planet 9 is real, a more plausible possibility is that it formed closer to the region of the giant planets and was later pushed outward by a powerful gravitational encounter. Instead of escaping entirely, it may have been retained on a distant orbit through the influence of the disk surrounding the young Sun or nearby stars within its birth cluster. In that scenario, Planet 9, if it exists, would be a surviving witness from a time when the solar system had not yet become stable. It would not merely add another planet to the list, but would reveal that planetary formation was once far more chaotic than the orderly arrangement we see today. A large world may have been thrown into the outer reaches, carrying gas, ice, and material from a region closer to the Sun, then continued moving through the darkness for more than 4 billion years. Until it is directly detected, Planet 9 remains a testable explanation. Models predict where in the sky to search, how bright the planet might be, and what kinds of orbits its gravity should produce. Each new survey may discover the planet itself, further narrow the region where it is allowed to hide, or uncover distant objects that change the entire orbital pattern. This is what keeps the hypothesis within science, rather than turning it into an idea that can never be disproved. It must continually face new evidence. Perhaps somewhere very far away, a large world is truly completing an orbit that lasts thousands of years, appearing in images as a faint point of light still unrecognized among a dense field of stars. Or perhaps no such planet exists, and the unusual orbits are only overlapping traces of stellar encounters, giant planet migration, and the limitations of present-day surveys. Both possibilities lead to the same lesson. The outer solar system is still not understood well enough for any single model to bring the story to a close. Planet 9 is therefore not the end of the journey, but a gap whose shape has been drawn by gravity. We have not seen this world, yet we know the regions of sky where it is unlikely to exist, the range of mass it would need to influence distant orbits, and the signs that should appear if its gravity is truly at work. Beyond the orbits that gave rise to this hypothesis, the solar system extends into a realm far larger still, where objects no longer form a disk around the Sun, but are distributed in a nearly spherical cloud. This is the distant reservoir of comets known only through the occasional visitors that fall into the inner solar system, a structure never observed directly, yet one that may reach almost to the gravitational boundary between the Sun and the surrounding stars. Beyond the distant orbit of Sedna and the hypothesis of an unseen planet, the solar system still does not come to an end. Far beyond that region may lie a structure vastly greater in scale, one that does not remain confined to a plane like the Kuiper Belt and does not form an extended scattered disk around the Sun. Its objects are thought to be distributed in many directions, creating a nearly spherical shell so sparse that a spacecraft could pass through without seeing a single body nearby, yet so immense that its total population may be enormous. This structure is known as the Oort Cloud. We have never photographed the cloud as a whole, nor have we directly observed an object while it was still within the most distant part of this realm. Its existence is inferred from the visitors that occasionally enter the inner solar system, long-period comets whose orbits are so vast that a single return may take thousands, tens of thousands, or even more years. These comets do not arrive from one common direction. Some enter from above the plane of the planets, some from below, while others travel at steep angles or even in the opposite direction. If their source were confined to a flat disk like the Kuiper Belt, most of their orbits should retain a clearer relationship with the common plane of the solar system. The fact that they appear from nearly every direction suggests that, at an immense distance, there must be a reservoir of material surrounding the Sun in 3 dimensions. In the middle of the 20th century, astronomer Jan Oort studied the orbits of long-period comets and noticed that many seemed to come from an extremely distant region before falling into the planetary system. He never saw this reservoir directly, but the motions of the comets suggested that they could not simply have been returning near the Sun again and again forever. Each time they enter the inner solar system, they are heated, gradually lose material, and have their orbits altered by the gravity of the planets. Without a distant source continually supplying new comets, the population should have been depleted long ago. From this idea, the image of the Oort Cloud began to emerge as a vast storehouse of icy bodies, where most members remain almost motionless on a human timescale, and only a tiny fraction are occasionally sent inward. The cloud may begin at distances thousands of times greater than the distance between Earth and the Sun, then extend outward for tens of thousands of astronomical units, reaching across a significant fraction of a light year. On this scale, the entire region containing the planets and the Kuiper Belt occupies only a small area near the center. Yet this vastness should not be imagined as a thick shell of ice surrounding the solar system. The Oort Cloud may be extraordinarily sparse, with distances between objects far greater than those familiar within the planetary region. Each body occupies only a tiny portion of this immense volume, while most of the space remains completely empty. The word cloud, therefore, describes how the population is distributed around the Sun, not a continuous mass of material that could be seen from far away. The members of the Oort Cloud are probably mostly small, icy bodies, similar to cometary nuclei that have never traveled close enough to the Sun to develop a glowing coma or tail. They may contain frozen water, carbon monoxide, carbon dioxide, methane, and many other volatile compounds preserved since the solar system was very young. Because they spend most of their time in deep cold and rarely experience intense heating, the material within them may retain more primitive traces than worlds that have been repeatedly altered closer to the Sun. What is especially remarkable is that the Oort Cloud probably did not form where it exists today. During the early stages of the solar system, small icy bodies formed near the region of the giant planets, where the disk surrounding the Sun was still dense enough to create countless objects. As Jupiter, Saturn, Uranus, and Neptune grew, their gravity began disturbing the paths of nearby bodies. Some were thrown inward toward the Sun. Some escaped the solar system entirely, while others were pushed onto orbits so broad that they traveled thousands of astronomical units away without completely losing their connection to the Sun. If planetary gravity were the only influence, many of these outward scattered bodies might still return to the planetary region and undergo further powerful encounters. But once their orbits expanded far enough, forces that were almost insignificant near the Sun began to matter. The overall gravity of the Milky Way, together with passing stars, could slowly alter the direction and shape of their orbits, raising their closest approaches to the Sun so they no longer returned to encounter the giant planets. In this way, an object that formed within a relatively flat disk could be carried outward and then stored on a tilted orbit for billions of years. Over immense spans of time, influences arriving from many directions gradually erased the population's original flat shape. Orbits tilted upward, downward, and spread more widely around the Sun until the outer portion of the reservoir became nearly spherical. This was not a transformation that happened all at once, but the result of billions of years of slow motion, with each gravitational pull producing only a slight change, but having enough time to accumulate. The Oort Cloud is therefore not completely still. A star passing at a relatively close distance may disturb part of the population, while the gravitational field of the Milky Way continually exerts a gentle influence on the most distant orbits. Most objects change only very slowly, but every so often, an orbit is adjusted in a way that lowers its closest approach to the Sun. The body then begins a long journey inward, moving faster as it enters the region where the Sun's gravity becomes stronger. For most of that journey, it remains only a dark block of ice with no obvious activity. Only when it comes close enough to the Sun does heat begin turning volatile substances on its surface directly into gas. That escaping gas carries dust with it, creating a hazy coma around the nucleus and forming a tail that extends away from the Sun. From that moment on, an anonymous object that once rested within the Oort Cloud becomes a comet visible from Earth. The brightness of a comet can make its appearance seem sudden, but that luminous phase occupies only a very brief part of its entire existence. Before arriving near the Sun, the object may have spent billions of years in the deep cold, while the journey from the distant Oort Cloud into the planetary region may itself have lasted millions of years. The weeks or months during which people see its tail in the sky are only the final, visible portion of a motion that began long ago. As a comet enters the planetary region, its orbit may continue to change. A single passage near Jupiter can shorten its period, redirect it onto a new path, or eject it from the solar system entirely. Some comets pass too close to the Sun and break apart, while those that return many times gradually lose their volatile materials, becoming darker and less active. Each object that leaves the Oort cloud may therefore appear in the inner solar system only a limited number of times before its orbit or physical structure is transformed completely. These comets provide the clearest evidence for a realm we cannot yet observe directly. Astronomers measure their positions and velocities as they enter the inner solar system, then calculate their orbits backward to estimate the distances from which they may have come. Tracing their paths into the past is not always simple, because the gravity of the planets and gases escaping from the surface can slightly alter a comet's motion. Even so, when many long-period comets point toward extremely broad orbits arriving from many different directions, the picture of a nearly spherical reservoir becomes increasingly convincing. This is an unusual way to study an invisible structure. Humanity cannot see the entire Oort cloud, but we can observe the rare members that leave it. From their directions of travel, the lengths of their orbits, and the patterns in which comets appear over time, we build a picture of the region to which they once belonged. It is not a detailed map with every object marked, but a model that best matches what the solar system continues to send into its inner regions. Our ability to observe an object directly while it is still within the Oort cloud remains extremely limited. At distances of thousands or tens of thousands of astronomical units, sunlight becomes far too weak for a small icy body to reflect enough of a signal back toward Earth. Its motion against the background stars would also be extraordinarily slow, while the region that must be searched covers nearly the entire sky. A world might already be present in the data, yet remain too faint to distinguish from the countless more distant sources behind it. For this reason, the true number of objects in the Oort cloud is still unknown. Estimates can vary considerably depending on the number of comets observed, models of how the planets once scattered material, and the proportion of bodies lost from the solar system over time. What is more certain is that the population must be large enough to continue supplying new long-period comets after more than 4 billion years, even though only an exceedingly small fraction is sent inward at any one time. The Oort cloud changes the way we imagine the edge of the solar system. If we consider only the planets, that edge seems to lie beyond Neptune. If we include the Kuiper Belt and the scattered disk, the map expands by tens or hundreds of astronomical units. But if we count every object still held by the sun's gravity, the solar system may extend across a vastly greater distance, nearly reaching the realm where the pull of neighboring stars begins to compete more clearly. There is no wall marking the place where the sun's influence ends. Its gravity simply weakens with distance, while the forces from the Milky Way and other stars become increasingly significant. The Oort cloud is therefore more like a broad frontier, where objects still orbit the sun but follow paths fragile enough to be altered by the interstellar environment over long periods of time. Seen from that distant realm, Pluto is nowhere near the final edge. It lies within a much smaller region surrounding the sun, while the orbits of the Oort cloud extend so far that a single revolution may last longer than the entire history of humanity. The comets that occasionally appear are only brief signals arriving from a reservoir of material we have never seen in full. Yet the Oort cloud gives us only one way to define a boundary, based on the objects that remain gravitationally bound to the sun. Beyond that frontier lies another kind of boundary, one that is closer but can be measured more directly, where the stream of particles continually flowing from the sun begins to slow and give way to the space between the stars. When we reach that region, we will no longer follow icy bodies along immense orbits, but the sun's own breath as it spreads into the surrounding darkness. The Oort cloud shows that the sun's gravity may reach far beyond the orbit of Pluto, but gravity is not the only sign of how far the central star's influence extends. The sun also continually releases its own material into space, creating a vast region that surrounds the planets, the asteroids, and the nearer reaches of the outer solar system. To find another kind of boundary, we do not need to keep following icy bodies along their immense orbits. We need only drift quietly with the stream of matter flowing away from the sun. Beyond the bright surface visible to human eyes, the sun's atmosphere is so hot that some of its material is no longer fully confined. Electrically charged particles escape, traveling through space at hundreds of kilometers per second and spreading outward in every direction. This flow is known as the solar wind, a name that sounds gentle, although it is not a current of air like wind on Earth, but an extraordinarily thin stream of plasma. Near the Sun, this flow is strong and fast, carrying the star's magnetic field outward with it. As it passes Earth, it interacts with our planet's magnetic field, helping create auroras, and sometimes making the space environment around us more turbulent. The solar wind then continues beyond the orbit of Mars, passes among the giant planets, crosses the region of Pluto, and spreads deeper into the darkness, where the distances between worlds grow ever wider. The entire region of space directly influenced by this flow of particles is known as the heliosphere. We can imagine the heliosphere as a vast domain inflated from within by the Sun, enclosing most of the familiar worlds of the solar system. This is only a simplified picture, because the true boundary is neither perfectly round nor completely still. It changes as solar activity strengthens and weakens, and it is shaped by the interstellar environment through which the entire solar system is moving. The farther the solar wind travels, the more thinly it spreads. The same amount of material must expand across an ever larger region, so the density and pressure of the particle flow gradually decline. For a long time, it continues outward almost freely, but eventually it encounters resistance from the extremely sparse matter between the stars. There, the Sun's breath does not disappear at once. It begins to slow, becomes compressed, and enters a more turbulent state. This transition does not resemble a wall that a spacecraft could see approaching from a distance. There is no distinct color, no bright line crossing space, and no moment when the surface of the spacecraft touches a dense layer of matter. The changes can be recognized only through instruments measuring the speed and direction of particles, the strength of magnetic fields, the density of plasma, and the number of high-energy rays arriving from outside. After the solar wind slows, it continues through a broad region before reaching the outermost boundary of the heliosphere. This boundary is called the heliopause, where the pressure of the particles flowing from the Sun is no longer strong enough to keep pushing the interstellar medium away. Inside the heliopause, matter and magnetic fields carry the Sun's signature more clearly. Beyond it, particles from the space between the stars begin to dominate. Even at the heliopause, the division is not perfectly sharp. Neutral atoms from the interstellar medium can pass inward, while particles originating from the Sun may still appear near the boundary. The two regions meet, interact, and alter one another, creating a transition zone much broader than the thin line often drawn in diagrams. For most of the history of this research, the heliopause was only a predicted boundary. Scientists knew that the solar wind could not continue expanding forever without meeting the environment beyond, but no instrument had traveled far enough to measure directly where that balance occurred. The opportunity came from two spacecraft launched in 1977, originally sent to study the giant planets, but ultimately carried farther than any functioning machines before them. Voyager 1 and Voyager 2 both flew past Jupiter and Saturn, while Voyager 2 continued onward to Uranus and Neptune. After those encounters, neither spacecraft turned back. Both continued outward along open trajectories. The giant planets gradually receded behind them, sunlight weakened, and radio signals sent back to Earth required many hours to complete the journey in one direction. The Voyager spacecraft were built in a technological era very different from our own, yet some of their instruments continued operating for decades. Their power supplies gradually weakened over time, forcing individual systems to be shut down one by one, so that the remaining energy could be reserved for the most important measurements. In the silence of the outer solar system, the two spacecraft continued sending back small streams of data, revealing that the environment around them was slowly changing. As Voyager 1 moved deeper into the outer heliosphere, its instruments recorded a decline in the number of particles originating from the Sun. At the same time, the intensity of cosmic rays arriving from the Milky Way increased as the spacecraft gradually left the protective region created by the solar wind and the Sun's magnetic field. The change did not occur in a perfectly simple way. Some signals rose and fell several times, requiring scientists to wait for more data before deciding whether the spacecraft had truly crossed the boundary. By 2012, more stable measurements showed that Voyager 1 had passed beyond the heliopause. Particles from the Sun dropped sharply, while high-energy particles from interstellar space remained at higher levels. No camera recorded a visible border, but the environment surrounding the spacecraft had changed clearly enough to confirm that it was no longer within the region directly dominated by the solar wind. 6 years later, Voyager 2 also crossed the heliopause, traveling in a different direction. The fact that the two spacecraft passed through the boundary at different locations helped reveal that the heliosphere is not a perfect sphere. Its shape and size depend on the direction in which the Sun is moving, the strength of the solar wind during different periods, and the pressure of the interstellar environment outside. Voyager 2 also carried an instrument capable of measuring the plasma around the spacecraft directly, providing additional information about how density changed as it moved from the inner side of the boundary to the outer side. These measurements showed that interstellar space contains more matter than the outer heliosphere, although the density is still far too low to resemble any familiar gaseous environment on Earth. The space beyond is not completely empty, but contains sparse particles, magnetic fields, and dust moving through the Milky Way. The moment Voyager crossed the heliopause is often described as the first time a human-made object entered interstellar space. That is true when we are speaking about the plasma environment, because the spacecraft had left the bubble created by the solar wind. Yet it had not left the solar system in the gravitational sense, because the Sun still holds objects at far greater distances, including members of the Oort Cloud. This distinction helps us understand why the solar system does not have a single edge. The heliopause marks the place where the Sun's breath gives way to the interstellar environment, while the Oort Cloud represents the distant realm where the star's gravity can still keep objects in orbit. A spacecraft can cross the first boundary within a few decades, but it would require thousands of additional years to reach the inner region of that much broader gravitational frontier. Voyager will no longer be operating when it reaches those distances. The power supplies of both spacecraft continue to weaken. Their instruments will gradually fall silent, and one day their final signals will no longer be sent back to Earth. After that, they will continue moving, carrying the golden records filled with sounds and images from the planet that created them, but with no way to tell us about the environment through which they are traveling. Even so, the distance Voyager has already covered has been enough to transform the way humanity sees the outer solar system. Before these crossings, the boundary of the heliosphere existed mainly in models and indirect observations. Now we have data from both sides. We know that the solar wind truly weakens, that cosmic rays become more abundant beyond the boundary, and that the interstellar environment near our solar system is not an absolute emptiness. The heliosphere also shows that the Sun does not exist in isolation from the rest of the Milky Way. As the star pushes material outward, the interstellar medium presses inward from beyond, and the shape of the Sun's domain is created by the balance between the two. If the Sun passes through a region of different density in the distant future, the heliosphere may contract or expand, causing the boundary crossed by Voyager to change as the entire star system continues its journey. All the familiar planets move deep within this region of influence. Earth, Jupiter, Neptune, and Pluto are all surrounded by material that began its journey at the Sun, although at the greatest distances, the flow has become too thin to be felt in any ordinary sense. For billions of years, the heliosphere has traveled with the Sun through the Milky Way, creating an environment of its own without ever becoming completely separated from what lies beyond it. When Voyager crossed the heliopause, it did not escape every influence of the Sun. It simply reached the place where particles from the star no longer dominated. Behind it lay a vast region sustained by the solar wind. Ahead lay the space between the stars, where matter no longer belongs exclusively to any single planetary system. By then, Pluto was already far behind, yet the gravitational edge of the solar system still lay ahead. This means that the journey from Earth to Voyager, longer than any voyage humanity has ever completed with a machine, still covers only a small fraction of the entire realm the Sun can call its own. The boundary of the heliosphere is therefore not an absolute ending, but a place where one influence becomes weaker than another. The Sun's breath does not suddenly vanish. It spreads thin, slows down, blends into the surrounding matter, and allows interstellar space to gradually take over. Beyond that boundary, space continues, thin and dark, but not entirely empty. Voyager is moving into that realm at an almost constant speed, carrying with it a small trace of a civilization that learned how to send an object beyond the region of space created by its own star. When Voyager crossed the boundary of the heliosphere, the spacecraft entered the interstellar environment, where matter is no longer directly dominated by the solar wind. That space is extremely thin, but not completely empty. Among the gas, dust, and magnetic fields may drift countless small objects that escaped the planetary systems where they first formed and now travel through the Milky Way on paths no longer bound to any single star. Most of these objects will never pass close enough to another star to be seen. They may drift through darkness for millions or billions of years, crossing distances so vast that no planet or telescope ever notices their presence. Yet every so often, one happens to pass through the solar system, entering a region where the light is stronger. For a brief time, humanity is given the chance to observe a fragment of matter that formed beneath the light of another star. These visitors are different from comets arriving from the Oort Cloud. A long-period comet may travel to enormous distances, but if its orbit remains closed around the Sun, it still belongs to the solar system. An interstellar object follows an open path, with a speed and direction showing that it was never previously bound to the Sun. It simply enters, accelerates as it approaches the star, changes direction under the influence of gravity, and then continues outward, never returning after one long revolution. The origins of such objects begin with planetary formation. Around a young star, gas and dust gather into a broad disk where small particles collide and gradually grow into rocky bodies, icy worlds, and eventually planets. This process does not unfold in complete tranquility. As large planets emerge, their gravity begins disturbing the countless smaller objects left within the disk. Some bodies collide with planets or remain trapped in distant belts. Others pass near a giant planet and gain enough energy to escape their central star. From that moment on, their paths no longer close around their original systems, but open into the space between the stars. Our own solar system probably lost many objects in this way, while Jupiter, Saturn, Uranus, and Neptune were still changing their orbits, so other planetary systems may also have released vast numbers of fragments into interstellar space. For a long time, the existence of this population was predicted only through models. Astronomers understood that giant planets could eject smaller bodies, but no object from another star system had ever been confirmed passing through our planetary region. That changed in 2017 when a survey in Hawaii detected a tiny point of light leaving the inner solar system along a path unlike any closed orbit. The object was named Oumuamua. When the measurements were combined, its orbit showed that it was moving too quickly to have been previously bound to the Sun. It had arrived from interstellar space, passed near the Sun, and continued outward on a journey that would never bring it back. Oumuamua was discovered relatively late, after it had already passed its closest point to the Sun and begun to fade. As a result, the observing window lasted only a few weeks, and the object never appeared as a clearly resolved world. Through telescopes, it remained only a point of light, but its brightness changed dramatically as it rotated, suggesting that its shape may have been highly elongated or unusually flattened compared with more familiar small bodies. Measurements also showed that Oumuamua's motion deviated slightly from the path gravity alone would have produced. A weak force appeared to be pushing it as it moved away from the Sun, yet there was no clearly visible cloud of dust like the one surrounding an ordinary comet. Gas escaping from the surface remains a natural explanation, although the type of material involved and the way the process occurred could not be determined with certainty from the limited data. Many possibilities were proposed to explain Oumuamua's shape, structure, and motion, but the opportunity to observe it ended before a complete answer emerged. Its greatest importance, therefore, lies not in its exact shape, but in its confirmed orbit. For the first time, humanity knew with certainty that an object formed beyond the solar system had passed through our region. 2 years later, another visitor appeared, but this time its nature was easier to recognize. The object was discovered in 2019 and named 2I/BORISOV, with the designation indicating that it was the second confirmed interstellar object. As Borisov approached the Sun, it developed a distinct cloud of gas and dust along with a visible tail, taking on the familiar appearance of an active comet. This difference allowed astronomers to study Borisov more directly. Light from the gas surrounding its nucleus was analyzed to identify the compounds escaping as surface ice warmed. The results showed that the object contained many substances also found in comets from our own solar system, while the proportions of certain materials displayed notable differences. This does not mean that Borisov was completely alien. On the contrary, its similarities suggest that the processes creating icy worlds may follow common patterns around many stars. The differences in composition merely indicate that Borisov formed in an environment with a different temperature, location, or chemical history from most of the comets we know. During its passage through the warmer region near the Sun, Borisov showed signs of breaking apart, as though its brief visit had altered an object that had spent most of its existence in deep cold. The remaining fragments then continued out of the solar system, carrying both the ancient history of the place where they formed and new traces from their encounter with another star. Oumuamua and Borisov were very different, and that difference reveals how diverse the interstellar population may be. One object showed almost no visible gas or dust, and was known mainly through subtle changes in reflected light. The other behaved unmistakably like an active comet. Between these two cases may exist many other kinds of bodies, from dark rocks and small fragments of ice to larger objects too rare to happen to pass close enough for us to see. The fact that only a few examples have been found does not mean interstellar objects are nearly non-existent. Most may be too small, too dark, or too distant during their passage to be detected. Even after entering the planetary region, a body may remain bright enough to observe for only a short time, while before and after that interval it may lie completely below the limits of our surveys. Oumuamua and Borisov are therefore probably only the first two recognized members of a much larger population. Wider and more sensitive surveys may discover more similar objects, especially if they can be found earlier while they are still approaching the solar system. A longer observing period would allow astronomers to measure their orbits more precisely, monitor surface activity, and analyze their composition before they once again fade into the distance. Even these first two discoveries, however, have already changed the way humanity views the space between the stars. Interstellar space does more than separate planetary systems. It also contains fragments of matter that once belonged to them. A small world can form within the disk around one star, be thrown outward by a giant planet, drift through the Milky Way for an immense span of time, and then appear beneath the light of another star. No message is carried intentionally, yet the material still preserves the history of the place where it was born. Its chemical composition, surface structure, and response to the warmth of the sun may all reveal something about a planetary environment beyond the reach of any spacecraft we can currently send. In that sense, interstellar objects are samples that come to us on their own. Humanity does not need to cross many light years to reach the star system where they formed, because sometimes a fragment from that distant place passes directly through our field of observation. The opportunity is brief, and the data are always incomplete, but every measurement extends planetary science beyond the boundaries of the solar system. These visitors also show that the boundaries between star systems are not completely closed. The solar system once scattered some of its own material into the Milky Way, while other planetary systems have also released small pieces into the shared space between the stars. Most will never meet, but occasionally their paths happen to cross, and an unfamiliar object passes through the sunlight of our system. For a few brief months, it appears as a measurable point of light. Then the distance grows, the signal fades, and the visitor returns to interstellar space, continuing on a journey whose destination we cannot clearly predict. Oumuamua and Borisov have moved far away, but their meaning remains. They showed that material from other planetary systems can reach our region, while also reminding us that the small worlds beyond Pluto may not remain bound to the Sun forever. Some will continue along stable orbits, some may become comets, and others will eventually be thrown outward and begin journeys between the stars. The space beyond is therefore not only a place where ancient objects are preserved, but also a realm from which small worlds can leave the systems that created them. Within that slow movement, every star holds on to part of its material while losing another part to the Milky Way, where those fragments continue drifting through the darkness until the light of an unfamiliar star happens to reveal them. After interstellar objects such as Oumuamua and Borisov passed through and faded from view, the sky returned to its familiar quiet appearance. The stars remained fixed, faint points of light continued to rest motionless in the images, and no obvious sign remained that a visitor from another planetary system had just crossed the realm of the Sun. Yet that quiet does not mean every object has already been recognized. Beyond Pluto, millions of small worlds may still be moving, most of them too faint and too distant to appear on our present maps. What we have not seen is not truly empty space. It is simply the portion of space that lies below the limits of our current instruments. An object may have orbited the Sun for more than 4 billion years without ever reflecting enough light toward Earth to be recorded. It may also lie in a region of sky that has received little attention, follow a steeply inclined orbit, or currently occupy the most distant part of its journey, where its brightness fades until it nearly blends into the darkness. These worlds send no signal to announce their locations. They quietly reflect only a tiny fraction of the Sun's light, then continue along their long orbits. To find them, astronomers must return to the same region of sky again and again, allowing time itself to reveal the difference. A distant star barely changes position between observations separated by several nights, while an object within the solar system shifts slightly against the background. Sometimes that movement amounts to only a few pixels, too subtle for the human eye to notice when each image is viewed alone. But when several images are placed side by side, one point of light begins to move, slowly but steadily enough to show that it does not belong to the background stars. From that moment, an unnamed object begins to enter the realm of human understanding. The first detection, however, is only the beginning. A point of light observed over a few nights does not immediately reveal the orbit it follows, its distance from the Sun, or how long it may take to return to the same region. Astronomers must find it again in later observations, extending its measured path piece by piece until they can gradually determine the route it follows around the Sun. This process may take months, and sometimes years, because distant worlds move too slowly for a small observed portion of their orbit to reveal its full shape at once. An object may belong to the relatively stable region of the Kuiper Belt, but it could also be traveling along an elongated path into the scattered disk, or even belong to the detached population represented by Sedna. Only after the orbit has been followed for long enough do these differences become clear. Some objects have been seen and then lost from the map, not because they left the solar system, but because their predicted positions gradually became too uncertain. If a body is observed for only a few nights before bad weather arrives or that region of sky moves out of season, the area in which it might later appear begins to expand. By the time telescopes return, the tiny point may have blended among millions of other sources and may remain lost for years before it is recovered. Mapping the outer solar system, therefore, does not unfold through one discovery after another in rapid succession. It follows a slower rhythm. Each world is secured through patient observations, with every new position connected to the last until the orbit becomes reliable. The map emerges not from clear lines visible from the beginning, but from countless points of light tracked across time. Future surveys will expand this process by covering larger areas of sky and returning to them more frequently. When the same regions are photographed over many years, objects beyond Pluto will no longer appear only as isolated discoveries, but gradually form a population that can be compared and studied. Brighter and nearer bodies will emerge first, while smaller or more distant worlds will begin to appear only when many layers of data are combined. The value of these new surveys does not lie in finding one uniquely remarkable object. More importantly, they can provide enough orbits for humanity to recognize what is common and what is truly unusual. One steeply inclined path may be an exception, but if dozens of bodies share the same feature, it may point to a gravitational process that acted in the past. Conversely, a group of orbits that once seemed carefully aligned may appear more random as the map becomes more complete. In this way, the questions raised throughout our journey can be tested more clearly. Are detached objects truly concentrated in a particular direction, or do they only appear that way because earlier surveys did not cover the sky evenly? How many large worlds remain hidden beyond Pluto? Do interstellar objects pass through the solar system more often than the first two discoveries suggest? Each answer will come not from a single image, but from the slow accumulation of observations across many years. When a new point of light is found, its orbit is only the first layer of information. Brightness alone cannot reveal its size with certainty, because a small object covered in reflective ice may shine more strongly than a larger world with a dark surface. To understand it more fully, scientists must combine other methods, measuring the faint heat it emits, analyzing the color of its reflected light, or waiting for it to pass in front of a star. Each measurement brings the picture into greater focus. The orbit reveals which region of the solar system the body belongs to and which gravitational forces may have shaped its path. Its color offers clues about the material on the surface. Its temperature helps distinguish a small, bright world from a larger but darker one. If a favorable occultation occurs, the object's shadow may reveal its true size and shape, and sometimes even a thin atmosphere or a structure surrounding the surface. A world, then, does not appear fully formed in our understanding at the moment of discovery. It enters human knowledge layer by layer, first as a moving point of light, then as an orbit, and later as a world with a size, color, and composition. Years may pass before a newly found object acquires a reasonably complete portrait, while the object itself continues the same slow journey it had followed long before anyone saw it. Only an exceedingly small number of these worlds will ever be visited by spacecraft. The distances are so great that each mission requires years of preparation followed by many more years of travel. Most bodies beyond Pluto will be known only through faint points of light, yet even those limited measurements can reveal the history of an entire region. Arrokoth was once just one such point before New Horizons flew past it. Seen up close, it appeared as two bodies joined together, preserving evidence of a very gentle merger from the youth of the solar system. Its example shows how much distance can conceal. An unremarkable point in a survey image may hold a shape, structure, and history that no one had predicted. Countless similar objects may remain beyond our view, not necessarily resembling Arrokoth, but each rich in information in its own way. Some may be paired bodies orbiting one another, some may retain tiny moons, and others may have elongated shapes produced by rapid rotation. Still, others may possess surfaces so dark that they have escaped detection through many surveys. Every object is the result of where it formed, the collisions it endured, and the gravitational influences it experienced over billions of years. A complete map, however, requires more than extraordinary cases. It also needs large numbers of ordinary objects, because they reveal the general structure of the outer realm. If we knew only Pluto, Eris, or Sedna, we would have a collection of remarkable worlds without understanding the populations to which they belong. When thousands of orbits are placed together, distinct groups begin to emerge, gaps acquire meaning, and the migration history of the giant planets can gradually be reconstructed. The blank portions of the map are therefore not entirely unknown, but neither can they be filled by only a few new discoveries. Each generation of telescopes will push the detection limit lower, revealing fainter objects and following them for longer periods. Yet beneath every new threshold, smaller or more distant bodies will continue to remain beyond our reach. There may never be a catalog containing every icy body orbiting the Sun. Their numbers are too great, their size is too small, and their distances too immense for such a task to be completed. But science does not need to observe every object individually to understand the population as a whole. From the portion seen clearly enough, humanity can estimate what remains, identify the major families of orbits, and learn how the outer solar system has changed over time. What matters is not making every dark region disappear, but understanding what that darkness may be hiding. The space beyond Pluto was once regarded as almost empty. Today, each new discovery reveals a region filled with dwarf planets, small icy bodies, scattered objects, detached worlds, and perhaps other populations that have not yet been fully recognized. In the years ahead, that map will continue to expand at a very slow pace. A point of light will appear, be found again, and gradually acquire an orbit. Another object will pass in front of a star and reveal its true size. A distant world will reflect a color never measured before, while somewhere else, another body will quietly leave the solar system and begin its journey between the stars. Each discovery adds only a tiny point, but when enough points are placed together, the emptiness begins to take on structure. Pluto is no longer a marker near the end of the map, but one of the first doorways into a realm far greater than anyone once imagined. And as that realm continues to emerge, what changes is not only the number of known worlds. The way humanity imagines the solar system itself also begins to shift, from a group of planets following orderly orbits into a vast system of overlapping layers, extending all the way into the environment between the stars. In the solar system maps once found in textbooks, Pluto often occupied the final position, with nothing beyond it but a dark background where the illustration came to an end. That arrangement was easy to remember, but it also created the impression that the solar system had a clearly defined boundary, as though crossing Pluto's orbit would bring every structure belonging to the Sun to an end, and interstellar space would begin immediately. The journey we have just taken reveals a far greater reality. Pluto is not alone beyond the planets, but moves within the Kuiper Belt, where countless icy bodies orbit the Sun along many different paths. Beyond the more densely populated part of that region lies the scattered disk, where Neptune has pushed many objects onto long and tilted orbits. Farther still are detached worlds such as Sedna, whose paths can no longer be explained easily by the direct influence of the outermost giant planet. Beyond those orbits, the map continues to expand. The Oort Cloud may surround the Sun in many directions, preserving countless icy bodies on journeys so long that a single revolution could far exceed the entire span of recorded human history. Closer than that distant realm, the heliosphere creates another kind of boundary, where the flow of particles from the Sun gradually weakens and gives way to the interstellar environment. Each of these regions might once have seemed like a candidate for the final edge, yet none represents an absolute ending. Neptune marks the outer limit of the major planets. The Kuiper Belt is a realm of many icy worlds. The heliopause reveals where the solar wind no longer directly dominates space, while the Oort Cloud may extend toward the region where the Sun's gravity becomes fragile against the influence of other stars. The question of where the solar system ends therefore has no single answer. It depends on what we are trying to measure. If we are speaking about planets, one boundary appears. If we are measuring the reach of the solar wind, another line is used. And if we include every object still held in orbit by the Sun's gravity, the map must expand thousands of times beyond the region containing Pluto. This complexity is not a flaw in the way science describes nature. The solar system truly does not end at a wall. The sun's different forms of influence simply weaken at different rates. Its light becomes more diffuse with distance. The solar wind is slowed by the interstellar medium, and gravity can continue holding objects in regions far more distant still. Instead of a thin edge, we encounter an immense transitional realm. There, populations of objects blend into one another, classifications become less rigid, and not every body fits neatly into a single group. Some worlds carry features of the scattered disk while also approaching the detached population, and an object such as Sedna is sometimes viewed as a bridge between the region beyond Neptune and the inner reaches of the Oort Cloud. Names help humanity organize its understanding, but the worlds themselves do not require boundaries in order to keep moving. They simply follow gravity, velocity, and the history of interactions that occurred long ago. An orbit may preserve the influence of Neptune, of a star that passed nearby when the sun was young, or of extremely slow forces acting within the environment of the Milky Way. Within this new picture, Pluto has not lost its meaning. It still possesses mountains of ice, plains of frozen nitrogen, a thin atmosphere, and a complex geological history. Only its place in the story has changed. Pluto no longer has to stand alone as the final point. It has become a large member of a much broader population. That change helps us understand Pluto more clearly rather than making it less special. Features that once made this world seem unusual, its small size, tilted orbit, and ice-rich composition, can now be understood within the context of the Kuiper Belt. Pluto has become a doorway into an entire realm rather than an object standing outside every other known structure. Most of the worlds in that distant region are far smaller than Pluto. Many are only irregularly shaped masses of ice, with no atmosphere and almost no change across billions of years. Yet their small size does not make their histories meaningless. Every orbit, color, and shape may preserve part of the story of how the original material gathered and how the giant planets rearranged the outer solar system. An object following a stable orbit may have avoided powerful encounters with Neptune. A body on an elongated path may once have been pushed outward by that planet. A detached world suggests that some additional influence raised the nearest point of its orbit away from the Sun. When many such objects are placed beside one another, their individual stories gradually combine into a shared history of the entire solar system. This is why the unseen portion remains so important. The known objects represent only a small sample, biased toward bodies that are large, bright, and fortunate enough to occupy favorable positions. Smaller and darker worlds, or those currently near the farthest points of their orbits, can easily remain beyond the limits of observation. When science suggests that millions of objects may exist beyond Pluto, it is not claiming that every member has been seen. The population is inferred from what surveys have detected and from the limitations those surveys have carefully measured. Most of those bodies will never receive individual names. They may never be visited by spacecraft, never appear in a clear image, and may exist only as a handful of points in a data set. Even so, their enormous numbers help answer questions that a few remarkable worlds cannot resolve. The proportions of different sizes, the distribution of orbits, and the gaps within the population can all reveal what happened while the solar system was still forming. New surveys will continue making the map denser, but the process unfolds very slowly. A point of light detected during the first few nights must be found again. Its orbit must be extended through months or years of observation, and only then can other measurements gradually reveal its size and composition. Worlds beyond Pluto do not emerge fully formed in a single moment. They enter human understanding one layer at a time. That slow pace is well suited to the region we are observing. There, a season may last for many decades, while a single orbit around the Sun may require hundreds or thousands of years. During the entire history of telescopic astronomy on Earth, a distant body may have traveled through only a very small fraction of its path. For this reason, the map we have today is incomplete, not only in space, but also in time. We observe these worlds during only a brief portion of journeys that last far longer. Some are seen while they are closer to the sun and therefore brighter, while similar members of the same population remain deep in darkness near the distant reaches of their orbits. Even as technology continues to improve, humanity may never create a complete list of every object beyond Pluto. The population is too large, and many bodies are too small for their reflected light to be detected from Earth. Yet science does not need to see each world individually in order to understand the outer region as a whole. From a sufficiently clear sample, we can still measure its broader structure, test different models, and recognize the families of orbits that have taken shape over billions of years. What matters is not making the darkness disappear completely, but understanding that darkness does not mean emptiness. Beyond Pluto, unseen worlds continue to move whether humanity has discovered them or not. They do not wait to be named, nor do they become more real after they are found. Telescopes simply carry them from the unknown into the realm of what can be measured. Looking back, the edge of the solar system has retreated many times. It once seemed to lie at Pluto's orbit, then expanded through the Kuiper Belt, the scattered disk, the detached objects, and the Oort Cloud. Voyager revealed another boundary in the reach of the solar wind, while Oumuamua and Borisov reminded us that matter can travel between star systems, crossing regions we often imagine as closed borders. The final edge, then, is not simply the place where one system ends, but where its influence gradually blends into a wider environment. Objects may remain bound, be scattered away, or happen to arrive from another star. The solar system does not stand apart from the Milky Way, but moves through a space where matter, gravity, and other histories are always present. Pluto no longer resembles the final point on the map. It is more like a marker near the beginning of the outer realm, where orbits grow wider and reflected sunlight begins to fade. Beyond it lie worlds already discovered, populations known only through inference, and dark regions still preserving much of the solar system's earliest history. Before this journey comes to a close, we can pause with that image. Pluto continues around the sun along its familiar path, while beyond it, countless unnamed bodies move slowly through the cold, preserving traces that have remained since the solar system was young. The human map has not reached the end, but the darkness beyond Pluto is no longer an empty space. It is a vast realm, still gradually coming into view. When we began this journey, Pluto appeared as a small world near the place where maps of the solar system once came to an end. In familiar illustrations, it often stood alone beyond Neptune, while the space farther out was shown only as a dark region with no name or clear structure. That view was not entirely wrong, but it reflected the limits of what humanity could observe at a time when most of the outer realm had not yet revealed its faint points of light. Today, Pluto no longer stands at the end of an empty road. It moves within a vast population of dwarf planets, small icy bodies, paired objects orbiting one another, and countless worlds that have never been named. Some remain on relatively stable paths within the Kuiper Belt. Others were pushed by Neptune onto elongated orbits, while still more distant worlds never come close enough to the Sun to return to the familiar region of the planets. Beyond those orbits, the Sun's influence continues outward in several different ways. Gravity may hold icy bodies within the Oort Cloud on journeys lasting hundreds of thousands of years, while the solar wind weakens and blends into the interstellar environment at a far closer distance. There is no single line marking the end of the solar system, because light, plasma, and gravity do not all fade away at the same place. What was once called the final edge has therefore become a broad transitional region, where the Sun's domain gradually blends into the Milky Way. Small bodies may remain bound for billions of years, be sent inward to become comets, or gain enough energy to escape the system entirely. At the same time, objects formed around other stars may pass through our region, appear briefly, and then continue their journeys through interstellar space. Within this wider picture, Pluto has not become less meaningful. On the contrary, it resembles the first doorway opened into the outer realm. When humanity saw its mountains of ice, plains of frozen nitrogen, and thin layers of haze, Pluto revealed that great distance does not mean simplicity. The other points of light discovered afterward continued to remind us that every object, even one far smaller, may possess a structure and history of its own. Some worlds are only a few kilometers across, too small for gravity to pull them into a round shape, and almost unchanged across billions of years. They may not possess vast landscapes or significant atmospheres, but the material within them formed from the same disk of gas and dust that created the planets. Each small body of ice is a remnant of that process, preserved in the deep cold after most of the material closer to the sun had been transformed. When many of these small objects are studied together, their orbits begin to recount movements that took place long ago. Populations held in resonance reveal Neptune's enduring influence. Scattered bodies preserve traces of past gravitational encounters, while detached orbits like Sedna's suggest that the outer solar system may once have been shaped by nearby stars or by a history that has not yet been fully understood. We still do not know exactly how many objects are moving beyond Pluto. The number depends on the smallest size included, the reflectivity of their surfaces, and the limits of each survey. Larger bodies are easier to detect, while small, dark objects may remain below the threshold of observation even if they have appeared in many images. The phrase "millions of worlds" is therefore not a completed list, but a scientific description of a population inferred from the portion we have seen. Of the millions of bodies that may exist, most will never be observed individually. They will receive no names, no close-up photographs, and may be represented only by numbers within a statistical model. Yet their existence still changes the way we understand the solar system, because a planetary system is made of more than its largest and brightest members. The major planets represent only a small part of the story. Around and beyond them lie populations of smaller bodies where the history of formation has been preserved in ways that the active surfaces of large planets can no longer retain. These objects connect the present with the youth of the Sun, when the disk of material had not yet settled into the relatively stable structure we see today. Perhaps the gentlest realization in this journey is that these worlds do not depend on humanity knowing about them. Before the first telescope was built, they were already moving along their long orbits. Before Pluto was discovered, the Kuiper Belt already existed. Before a spacecraft crossed the heliopause, the solar wind had always slowed at the boundary with interstellar space. Science does not create these regions. It only allows them to emerge gradually within human understanding. A point of light recognized among millions of background stars, an orbit extended through years of observation, or the dimming of starlight for a few seconds can each bring another part of the darkness onto the map. Such discoveries often begin as something very small, but when placed together, they can transform the entire picture of the place we inhabit. The map of the solar system is therefore not a finished image, but a structure that continues to expand over time. Regions once considered empty have become densely populated realms. Objects once treated as exceptions have later been recognized as members of broader families. Each time our understanding changes, the imagined edge moves farther away. Not because the solar system has suddenly grown, but because humanity has seen another part that was always there. Future surveys will discover more slowly moving points of light. Some will simply add new members to known populations, while others may follow orbits unusual enough to force current models to change. A large world may still be hidden in the farthest regions, or new observations may show that the patterns once suggesting its existence were only the result of incomplete data. Whatever the final answer may be, the map will become more accurate. Some objects will be discovered while moving through the nearer portions of their orbits, then fade again for centuries. Interstellar visitors may appear for only a few months before leaving the solar system forever. These events remind us that the human window of observation is extremely brief compared with the rhythms of the outer realm, where a single orbit may last longer than the entire history of many civilizations. Across these immense timescales, Earth still completes one revolution around the Sun each year, while Pluto requires nearly 2.5 centuries to return to the same position. Farther away, Sedna follows an orbit lasting more than 10,000 years, while the outermost members of the Oort Cloud may require hundreds of thousands of years. These motions are extraordinarily slow from a human perspective, but they have never stopped. At this very moment, unseen worlds are continuing their journeys. Some are traveling through portions of their orbits where the light is too weak for telescopes to detect them. Some lie in regions of sky that have not yet been surveyed deeply enough, while others are so small that they may never appear in an image. They remain under the pull of the sun, still carrying material formed in the beginning, and still contributing to the true structure of the solar system. When we imagine this realm, we do not need to picture every object individually. It is enough to think of a vast expanse, where sunlight gradually weakens without disappearing completely. Within that faint illumination, countless icy bodies move slowly along their own paths, occasionally passing in front of a background star or reflecting just enough light for a telescope on Earth to notice. A tiny point of light is discovered, then followed over many nights. An orbit begins to emerge, its distance is estimated, and a world that was once completely unknown enters the map. Many more unseen points remain beyond it, but each new discovery makes the darkness a little easier to understand. Perhaps this is the fullest answer to the question that carried us through the entire journey. Beyond Pluto, there is not an empty space, nor merely a handful of remarkable objects. There is a vast realm of layered structures, many kinds of orbits, and perhaps millions of small worlds, most of which have never been directly seen by human eyes. Pluto is not the end. It is where the old map once stopped, and where a larger map begins to unfold. Far away, that world continues moving among the other bodies of its region, while sunlight travels billions of kilometers to touch its frozen surface and reflect back into space. Beyond Pluto, wider orbits continue to open. Unnamed objects keep circling through the darkness, and the solar system still holds many stories that have yet to be read. Thank you for joining Sleep Gravity on this journey, from the world once considered the final frontier to the vast regions where the map still contains so many blank spaces. Now, as Pluto and the distant worlds continue their slow revolutions around the sun, you do not need to remember every number or every name we encountered. Simply hold on to the feeling that beyond everything we can see, there is always a wider, quieter space still waiting to be understood. As those icy worlds continue moving through the darkness, allow your thoughts to slow as well. The light may grow faint in the outer reaches, but the orbits continue with quiet persistence, never hurried and never needing a clearly defined end. May you have a peaceful night, a deep and restful sleep, and until we meet again on another journey with Sleep Gravity,